The Bootstrap Paradox. A book appears on your desk. No title, no author. Flipping through the pages, you realize it contains incredible knowledge, secrets of the universe, advanced mathematics centuries ahead of its time. Driven by curiosity, you begin to study it, mastering its contents over years. Eventually, you decide the world must see this knowledge, so you publish the book yourself. It spreads, passing from generation to generation, until one day, centuries later, a worn copy ends up back in your hands, the very same book you once found. The question is, who wrote it? This is the Bootstrap Paradox, a time loop where something exists without an origin. A piece of information, an object, or even a person seems to emerge from nothing, passed through time in a cycle with no clear point of creation. Unlike other time paradoxes that involve altering the past, the Bootstrap Paradox suggests that something can exist without ever being created at all. Imagine a violinist who travels back in time and teaches their younger self to play. That younger version grows up, becomes the same violinist, and eventually travels back again, completing the loop. But if no one outside the loop ever taught them, where did the knowledge of playing the violin originally come from? It has no true beginning. It simply exists in an endless loop, violating our understanding of causality. The paradox gets its name from the phrase, pulling yourself up by your own bootstraps, an impossible act of self-creation. It shows up in science fiction all the time, like in stories where a person receives a blueprint for a futuristic machine, builds it, and later travels back to give that same blueprint to their past self. The machine is real, it functions, but who actually designed it? If the knowledge always existed within the loop, then it has no definitive creator. Physics doesn't completely rule out bootstrap paradoxes, especially in theoretical models of time travel. In a universe where closed time loops exist, events could sustain themselves without ever needing an initial cause. Some interpretations of quantum mechanics even suggest that information might be preserved across time in ways we don't fully understand. If this paradox is possible, then some of the most fundamental truths we take for granted might not be as certain as we believe. After all, if a book, a violinist, or a machine can exist without a creator, who's to say the universe itself didn't emerge the same way? The paradox of the unexpected hanging. A prisoner sits in his dimly lit cell, awaiting his fate. The warden arrives with an announcement. You will be hanged at noon on a weekday next week. However, the execution will be a surprise. When the hangman arrives, you will not see it coming. The prisoner, a man of sharp logic, begins analyzing the statement. He reasons that if he can predict the day of his execution, it cannot happen, because the warden's condition of surprise would be violated. So he begins to dismantle the possibilities. First, he considers Friday. If he is still alive by Thursday night, then Friday must be the day. But if he knows this in advance, then the execution won't be a surprise. Therefore, Friday is impossible. But if Friday is ruled out, then Thursday becomes the last possible option. And if he is still alive by Wednesday night, then the execution must happen on Thursday, making it predictable, which contradicts the warden's condition. So Thursday is impossible too. The prisoner follows this logic backward, eliminating Wednesday, Tuesday, and finally Monday. By the end of his reasoning, he is convinced his execution cannot logically take place. He leans back against the cold stone wall, satisfied that he has escaped his fate with nothing but logic. Yet come Wednesday at noon, the hangman arrives. The prisoner is dragged to the gallows, completely blindsided. The warden's decree has been fulfilled. The execution was both inevitable and a total surprise. This is the paradox of the unexpected hanging, a riddle that warps reason into contradiction. The prisoner's mistake? He assumed that logical deduction could dictate reality. But paradoxically, his very reasoning, his certainty that he could predict the outcome, became the thing that ensured his surprise. This paradox exists in many forms. In academia, it takes shape as the surprise exam paradox. A professor tells students that there will be a pop quiz next week, but they won't know the day. The students, reasoning like the prisoner, attempt to prove that the test cannot occur. Yet when the professor hands out the quiz mid-week, they are shocked. The paradox plays out in the real world, again and again, as people attempt to predict the unpredictable, only to be caught off guard when events unfold differently. But the implications go deeper. The paradox challenges the reliability of logic itself. The prisoner's reasoning was flawless in isolation. Each step followed logically, but the final conclusion was completely wrong. How can flawless reasoning lead to a false outcome? It reveals something disturbing about certainty. The more convinced we are that we can predict the future, the more vulnerable we become to unexpected events. Just because something seems impossible on paper does not mean reality will abide by those constraints. It also raises a larger question. Can surprise and certainty coexist? If an event is guaranteed to happen, does it lose its ability to be unexpected? And if we assume we can always predict what will happen next, do we set ourselves up for greater shocks when reality defies our expectations? Perhaps that is the true warning hidden in the paradox. The most dangerous surprises are the ones we believe we have ruled out entirely. Zeno's paradoxes. You stand at the starting line, ready to cross the room. The distance is short, just 10 steps. You take your first step, then another. But what if someone told you that reaching the other side was logically impossible? This is the strange world of Zeno's paradoxes, a series of ancient thought experiments that challenge the very idea of motion itself. Over 2,000 years ago, the Greek philosopher Zeno of Elea proposed these paradoxes to prove a shocking claim. Movement is an illusion. The most famous of these paradoxes is Achilles and the tortoise. Imagine the legendary Greek warrior Achilles, the fastest runner of his time, competing in a race against a slow-moving tortoise. To make it fair, the tortoise is given a head start. Now, as Achilles begins running, he quickly reaches the spot where the tortoise used to be. But by then, the tortoise has moved forward a little. Achilles reaches this new spot, but by the time he gets there, the tortoise has advanced again. This continues indefinitely. Each time Achilles arrives at the tortoise's previous position, the tortoise has moved slightly ahead. If Achilles must first reach an infinite number of points where the tortoise previously stood, how can he ever overtake it? Another version, the dichotomy paradox, follows the same logic. Before you can walk across a room, you must first cover half the distance, then half of what remains, then half of that. Since this process continues forever, it seems you should never complete your journey. How can you move at all if an infinite number of steps must be taken first? Zeno's argument appears airtight. The logic is sound, yet the conclusion is absurd. We know Achilles will overtake the tortoise. We know we can cross the room, so what went wrong? For centuries, philosophers and mathematicians wrestled with these paradoxes. Some dismissed them as word games, but others saw them as serious challenges to our understanding of reality. The paradoxes raise a deeper question. Is motion real, or is it just an illusion created by our minds? The key to resolving Zeno's paradoxes lies in infinity itself. The mistake is in assuming that an infinite number of tasks must take an infinite amount of time. In reality, the infinite sequence of smaller and smaller steps converges to a finite sum. Mathematics eventually caught up with philosophy. The development of calculus, most notably by Isaac Newton and Gottfried Wilhelm Leibniz, provided a solution. The concept of limits showed that an infinite number of steps could sum to a finite result. Achilles does pass the tortoise. You do cross the room. Motion is possible, even in a world where infinity lurks in every step. Yet, some remain unsettled. If movement is just a series of infinite divisions, does reality continuously flow, or is it made up of discrete frames, like individual moments frozen in time? Some interpretations of quantum mechanics suggest the universe itself may not be smooth, but composed of indivisible units at the smallest scales. In this case, Zeno may have been onto something far deeper than he ever realized. Zeno's paradoxes serve as a reminder that even the most ordinary experiences, walking, running, moving, contain mysteries that can unravel our understanding of reality. Is motion just an illusion of perception? Are we living in a universe where change is merely a mathematical construct rather than a physical truth? And if we can question something as fundamental as movement, what else might turn out to be an illusion? The liar paradox. A simple sentence stands before you. Nothing complex, nothing elaborate, just 4 words. This statement is false. You pause, reading it again. Something feels off. If the statement is true, then it must be false. But if it's false, then it must be true. Welcome to the liar paradox, an ancient logical riddle that refuses to be resolved. It's a sentence that should be easy to classify as true or false, yet the moment you try, you're pulled into an infinite loop of contradiction. The paradox dates back to at least the 4th century BCE, attributed to Eubulides of Miletus, a Greek philosopher who specialized in self-referential puzzles. His original version was simple. A man says he is lying. If he is lying, then he is telling the truth. But if he is telling the truth, then he is lying. This might seem like an amusing wordplay, but the implications run deep. The liar paradox exposes cracks in the foundations of logic itself, a fault line that mathematicians, philosophers, and even computer scientists have struggled to mend. At first glance, it seems like the paradox is just a clever trick. Maybe we should ignore it, dismissing it as meaningless nonsense. But logic doesn't work that way. Every sentence must be either true or false. No exceptions. The liar paradox breaks this rule, creating a statement that cannot logically exist, yet clearly does. One way to escape the paradox is to claim that truth and falsehood are not the only possibilities, that some statements exist in a strange in-between state. Some logicians propose truth gaps, where a sentence is neither true nor false. Others suggest truth gluts, where a statement is both true and false at the same time. Neither solution is satisfying. If logic allows for statements that are both true and false, can we trust any logical system at all? For most of history, paradoxes like this were little more than intellectual curiosities. But in the early 20th century, they exploded into a full-blown crisis. Bertrand Russell, one of the greatest logicians of all time, discovered that self-referential paradoxes, like the liar paradox, weren't just fun puzzles. They were fundamentally breaking mathematics. Russell's discovery forced the mathematical world into an existential crisis. What if all of mathematics was built on unstable foundations? The response was a radical shift in the way we understand logic, leading to new systems that tried to contain paradoxes rather than resolve them. Mathematicians like Kurt Gödel took the lesson even further, proving that some truths will always be beyond our reach, that even the most perfect logical system contains statements that can never be proven. The liar paradox doesn't just threaten mathematics. It also haunts computer science, linguistics, and even artificial intelligence. Any system that relies on logic must contend with the problem of self-reference. If a machine encounters a version of the liar paradox, what should it do? Some AI researchers worry that self-referential loops like these could cause AI systems to lock up, crash, or produce unpredictable results. If a machine is programmed to analyze truth but encounters a statement that defies categorization, how does it respond? Even beyond AI, the paradox seeps into philosophy and epistemology, the study of knowledge itself. If we can't even define truth and falsehood with absolute certainty, how can we trust any statement at all? The liar paradox is more than just a curiosity. It is a crack in the very structure of thought. It challenges the basic assumption that words and logic can map onto reality in a consistent way. And if something as simple as a single sentence can throw our entire system of reasoning into disarray, what else might be lurking in the depths of our understanding, waiting to unravel everything we believe to be true? The ship of Theseus Paradox. A legendary ship rests in a harbor, preserved for generations. Over the years, its wooden planks begin to rot. Slowly, piece by piece, They are replaced, first a mast, then the sails, then entire sections of the hull. Decades pass until every single part of the ship has been swapped for a new one. And then comes the question that philosophers have struggled with for over 2 millennia. Is it still the same ship? This is the ship of Theseus paradox, an ancient thought experiment that challenges our deepest intuitions about identity, continuity, and change. First recorded by Plutarch, a Greek historian from the 1st century AD, the puzzle asks, if every part of something is replaced, is it still the same thing, or has it become something else entirely? At first, the answer seems obvious. Of course, it's still Theseus' ship. The process of repair was gradual, and at no point did it suddenly cease to be itself. But the paradox doesn't end there. Imagine that every removed plank from the original ship is carefully stored, preserved, and reassembled elsewhere. Over time, a second ship, identical to the original in every way, comes into existence. Now we have 2 ships, one made of entirely new parts but continuously maintained, one made of the original planks, reassembled in the same shape. Which one is the real ship of Theseus? Some argue that the ship that remained in the harbor is the original. It never disappeared, and its function and identity were preserved. Others claim that the reassembled ship, built from the original materials, is the true ship. After all, if you saw a person slowly fade away and another person appear with their exact body parts, wouldn't you assume the second one is the same as the first? This is where the paradox grips us. Both answers seem correct, yet they contradict each other. At its core, the ship of Theseus is about what it means for something to remain itself over time. And it's not just a problem for ships. This paradox applies to everything, including you. Every cell in your body is constantly dying and being replaced. In a span of several years, nearly all the atoms that make up your body have been swapped out. Are you still the same person you were a decade ago? If the answer is yes, then what exactly makes you you? Is it your physical matter or something else? Your memories, consciousness, and continuity of experience? Neuroscientists and philosophers debate whether personal identity is tied to physical continuity or the persistence of thought. Some argue that a person is not their body, but rather a pattern of information, a continuity of memory and self-awareness, rather than a specific collection of molecules. The ship of Theseus paradox isn't just a historical puzzle. It has real-world consequences in fields ranging from law and medicine to artificial intelligence and physics. Consider organ transplants and medical advancements. If a person undergoes multiple organ transplants, synthetic limb replacements, or even a future scenario where their consciousness is uploaded to a machine, at what point do they stop being themselves? What about corporations and institutions? A company might replace every employee, change its leadership, and rebuild its offices, yet still claim to be the same organization. But if every defining feature has changed, is it truly the same entity? Even in the realm of artificial intelligence, the paradox looms. If an AI system undergoes continuous upgrades, replacing every line of its original code while retaining its function, is it still the same intelligence? There is no single answer to the ship of Theseus paradox. Some suggest that identity is not absolute, but a fluid, evolving concept. Things don't have a single true essence, but rather a shifting continuity that we recognize. Others argue that identity is merely a convenient illusion, something we impose onto an ever-changing reality to make sense of the world. But whether applied to ancient ships, human consciousness, or the future of artificial intelligence, one thing remains clear: everything changes. And in a world where nothing remains the same forever, what does it truly mean to exist? Quantum Immortality Paradox. A gun is aimed at your head. It is connected to a quantum device, one that measures the spin of a subatomic particle. If the particle spins one way, the gun fires. If it spins another, the gun does nothing. The trigger is pulled. But no matter how many times the experiment runs, from your perspective, the gun never goes off. Every time the quantum measurement is made, you find yourself in the universe where you survive. You live. again and again and again. This is the unsettling implication of quantum immortality, a thought experiment tied to the many worlds interpretation of quantum mechanics. It suggests that as long as there is some possible branch of reality where you continue to exist, you will always experience that branch, never the ones where you die. From an external perspective, the experimenter may see the gunfire in half of all universes, meaning many versions of you perish instantly. But for the conscious observer, the one experiencing reality firsthand, death is something that happens only to other versions of you, never to the one doing the observing. It all begins with the Schrodinger's cat paradox, where a cat in a box exists in a superposition of both alive and dead states until observed. The many worlds interpretation takes this a step further. Instead of the wave function collapsing into one definitive outcome, reality itself splits. The cat is alive in one universe and dead in another, both existing simultaneously. Apply this to a human observer, and the implications become even more bizarre. If consciousness follows the path where survival is possible, does that mean death is always something that happens to other people, other versions of yourself? Could an individual experience a subjective immortality, never encountering an end to their own existence, but instead waking up in increasingly improbable realities where they somehow persist? It wouldn't mean aging indefinitely or avoiding misfortune. It would mean that, no matter the odds, you always find yourself in the version of events where you survive. The universe conspires, not by design, but by sheer probability, to ensure your continued existence. At first, this seems absurd. We see death all around us, an unavoidable consequence of life itself. But from a first-person perspective, have you ever actually experienced the moment of your own death? You have no memory of ceasing to be, only of continuing. Quantum immortality suggests that this trend will never stop. Even if it requires the most improbable chain of events, miraculous recoveries, freak accidents that should have killed you but didn't, bizarre cosmic coincidences that keep pushing you forward, you will always find yourself in the reality where you are still alive. But what kind of existence would that be? Suppose you are on the brink of death, hooked up to life support in a hospital, barely functioning. If quantum immortality holds true, then even in the most desperate conditions, there will always be one timeline, however improbable, where you linger on. Consciousness persists, no matter how frail the body becomes. The nightmare scenario emerges. What if you do not continue in a healthy state, but in an unrecognizably damaged, decaying form, trapped in an unending, deteriorating existence with no release? And then there's the other side of the equation. Even if quantum immortality ensures you never experience your own death, it does nothing to stop the loss of others. You will continue living, but those around you will still vanish, one by one. The world will keep shifting, timelines diverging, but each version of reality will still be marked by loneliness, by the gradual erasure of familiar faces. Of course, this entire idea hinges on the validity of the many worlds interpretation. If the universe does not split with every quantum event, if wave functions truly collapse instead of branching into alternate realities, then quantum immortality collapses with it. Death in that case is final, just as we have always assumed. But if the many worlds interpretation is correct, and every possibility plays out somewhere, then in at least one version of reality, your story never ends. You simply continue forward, always surviving, always waking up to another day, even when the odds dictate otherwise. And if that is true, the question is no longer if you will live forever, but how long you will endure before you wish you hadn't. The Grandfather Paradox. You step into a time machine, the hum of hidden energy vibrating through the metal walls. The past stretches before you, an open book waiting to be rewritten. But what happens if, in your journey backward, you do the unthinkable, erasing your own lineage before it even begins? Could you still exist to make that choice, or have you just created an impossible contradiction, one that defies the very nature of time itself? The Grandfather Paradox is one of the most famous problems in time travel philosophy, a logical knot that tightens the moment you try to unravel it. Suppose you go back in time and prevent your grandfather from meeting your grandmother. If you succeed, one of your parents is never born, which means you are never born. But if you were never born, then how did you ever go back in time in the first place? The paradox loops endlessly, spiraling into an absurd impossibility. The contradiction seems straightforward, but the implications stretch far beyond a simple thought experiment. If time travel to the past were possible, it would mean that causality, the principle that every effect has a cause, could be broken. The very foundations of logic and physics would crumble under the weight of an action that erases its own cause. And yet the concept of time loops, altered histories, and self-negating events has fascinated philosophers and scientists alike. One possible resolution to the paradox is that nature itself prevents such contradictions. This idea, known as the Novikov self-consistency principle, suggests that time might work in a way that avoids paradoxes altogether. If you travel to the past, you may still interact with events, but only in ways that preserve the future that led you there. Every attempt to change history would be subtly corrected, leading to the same outcome, perhaps a series of chance accidents preventing you from ever meeting your grandfather, or ensuring that your actions somehow lead to his fate remaining unchanged. But what if the universe is less rigid? Some theories propose that every action creates a branching timeline, meaning that if you were to alter the past, you wouldn't erase your own existence. You would simply create a separate reality where you never existed. This many-worlds interpretation of quantum mechanics suggests that parallel timelines constantly diverge from every possible choice, meaning your trip to the past wouldn't change the reality you left, but would instead spawn an alternate history where a version of you never came to be. This raises further unsettling questions. If infinite timelines exist, does that mean every possible version of events has played out somewhere? Are there countless versions of you, each navigating their own fate, unable to alter the path of another? Or do timelines collapse back into coherence, leaving only one stable history behind? Some theorists suggest that time might not be a simple sequence of events, but rather an illusion with all moments past, present, and future existing simultaneously. This block universe theory views time as a landscape, where traveling backward wouldn't allow you to rewrite reality, but merely to observe a fixed past, like walking through a museum of frozen moments. And yet, the paradox refuses to die. If the past is set in stone, does that mean free will is an illusion? If multiple timelines exist, does every choice spawn infinite new realities? If contradictions must be avoided, does that mean time itself is self-correcting? The Grandfather Paradox sits at the heart of these mysteries, an unresolved enigma that stretches the limits of what we think we understand about reality. For now, time travel to the past remains a concept of fiction, locked behind the constraints of relativity and causality. But if the day ever comes when a machine can transport someone backward through history, one question will remain: will they be a traveler, an observer, or a paradox waiting to happen? The Banach-Tarski Paradox. A sphere sits before you, perfectly round, solid, and unbroken. You reach out, take it apart, and somehow you now hold not one, but two identical spheres. No stretching, no shrinking, no loss of material. You started with one object, and now you have two, each identical to the original. No laws of physics were broken, and yet something deeply unsettling has just occurred. This is the Banach-Tarski Paradox, a mathematical enigma that defies intuition and bends reality to its breaking point. At its core, the paradox states that, under the right conditions, a solid sphere can be divided into a finite number of pieces and reassembled into two identical copies of itself without adding or removing any material. It is an absurd proposition, one that suggests infinite creation from nothing, as if you could take an apple, break it apart, and reconstruct two apples of the exact same size. If this were possible in the physical world, it would mean infinite matter could be generated from a single object, defying the conservation of mass and energy. The paradox emerges from the strange world of set theory and higher-dimensional mathematics. In the early 20th century, mathematicians Stefan Banach and Alfred Tarski demonstrated that, using the principles of geometric decomposition, a three-dimensional object could be divided and rearranged in such a way that its total volume doubles. The process relies on an unsettling fact about infinite sets in the abstract realm of mathematics. Objects do not behave as they do in reality. This mind-bending result stems from a branch of mathematics called measure theory, which studies how to assign volume to shapes. In the real world, objects have well-defined measurements, length, area, and volume. But in the abstract world of pure mathematics, things get murky. The pieces into which the sphere is divided are not ordinary fragments but infinitely complex, non-measurable sets, so intricate that they have no defined volume on their own. When these fragments are reassembled in just the right way, they form two complete spheres, as if volume itself had been conjured from thin air. Of course, there is a catch. The Banach-Tarski Paradox is purely a mathematical result. It cannot be performed in the physical world. The construction requires breaking an object into an infinite number of infinitely complex pieces, something that is impossible with real-world atoms and molecules. Physics imposes strict limitations on how matter can be divided and rearranged, but the paradox still raises deep philosophical questions. If mathematics is supposed to describe reality, how can it produce results that seem so utterly impossible? And if our understanding of space, volume, and measurement is based on mathematical principles, what does it mean when those principles allow for such contradictions? One unsettling implication of the paradox is its connection to the concept of infinity. The universe, as vast as it is still thought to be bound by the conservation laws of physics. But if an infinite process could be realized, could infinite energy or matter be extracted from a single source? Does the paradox suggest a deeper hidden structure to reality, one where space itself might behave differently at fundamental levels? Even in mathematics, not everyone is comfortable with the implications of the Banach-Tarski Paradox. It relies on the axiom of choice, a controversial assumption in set theory that allows for the selection of elements from infinite sets without a clear rule. Without this axiom, the paradox collapses, but so too do many other useful results in mathematics. It is a trade-off between accepting a deeply unsettling conclusion or abandoning powerful mathematical tools. The paradox remains one of the most profound and disturbing results in modern mathematics. It suggests that the world we see and the rules we take for granted may be mere approximations of a deeper, more paradoxical structure. If mathematics is the language of the universe, then somewhere, in some incomprehensible way, the logic of the Banach-Tarski Paradox might be woven into the very fabric of existence. And if that is true, what else might be possible? The Omnipotence Paradox. Can an all-powerful being create a rock so heavy that even they cannot lift it? It's a simple question, almost childish in its phrasing, yet it cuts straight to the heart of an ancient contradiction. If the being can create such a rock, then there is something they cannot do, lift it. But if they cannot create the rock, then their power is already limited. Either way, omnipotence seems to collapse in on itself. This is the Omnipotence Paradox, a dilemma that challenges the very concept of unlimited power. At first glance, omnipotence appears to be an absolute quality, the ability to do anything without restriction. But once examined, cracks begin to appear. If omnipotence means truly limitless power, then it must include the power to limit itself. Yet, if an omnipotent being can impose limits on its own abilities, then in doing so, it ceases to be omnipotent. The paradox reveals a contradiction. Can infinite power contain itself, or does it inevitably break under its own weight? The roots of this dilemma stretch back to the earliest theological and philosophical debates. Medieval scholars wrestled with the idea of divine omnipotence, attempting to define it in a way that avoided logical inconsistencies. The problem lies in whether omnipotence should be understood as the ability to do anything imaginable, or only the ability to do anything that is logically possible. If omnipotence must include the ability to do the logically impossible, such as creating a square circle or making 2 + 2 = 5, then it becomes meaningless, a concept that defies reason itself. One solution proposed by philosophers like Thomas Aquinas was that omnipotence does not include the ability to do the logically contradictory. Under this view, asking whether an omnipotent being can create a rock too heavy to lift is like asking whether they can make an illogical statement true. The paradox, then, is not a real problem. It is merely a linguistic trick, a misunderstanding of what omnipotence actually means. But does this truly resolve the issue, or does it simply redefine omnipotence to avoid paradox? Another approach suggests that omnipotence is a dynamic state rather than an absolute one. A being might have the ability to do anything possible at a given moment, but if they choose to limit themselves, that limitation does not contradict their power. It is an expression of it. In this way, omnipotence could be seen as a shifting concept, one that allows for self-imposed restrictions without eroding its fundamental nature. But this interpretation raises new questions. If an omnipotent being can restrict itself, can it ever undo those restrictions? And if it cannot, is it truly omnipotent anymore? The implications of the omnipotence paradox go beyond theology. It forces us to question the nature of power itself. Can any system, being, or force ever be truly limitless? Even in physics, constraints seem to emerge naturally. Energy cannot be created or destroyed. Motion follows precise laws, and causality enforces a strict order upon events. If omnipotence is impossible, even in theory, does that suggest that no force, no matter how vast, can ever escape the fundamental boundaries of logic? This paradox also has eerie parallels in human history. Rulers, empires, and ideologies have often sought absolute control, only to find themselves bound by contradictions of their own making. The more power they accumulate, the more resistance they create. The more they try to control, the more unstable they become. If omnipotence is self-defeating, then perhaps every pursuit of ultimate power is destined to unravel under its own weight. In the end, the Omnipotence Paradox is not just about gods, rocks, or the limits of divine power. It is about the tension between possibility and impossibility, the recognition that no force, natural, supernatural, or theoretical, can escape the fundamental constraints of existence. And if even the concept of limitless power collapses under scrutiny, what does that say about the very structure of reality itself? The Sorites Paradox. A single grain of sand is not a heap, that much seems obvious. Add another, and it's still not a heap. Keep adding grains, one by one, and at what point does a mere collection of sand become an actual heap? The transition is impossible to pinpoint, yet a heap undeniably exists. Now reverse the process. Start with a heap, remove one grain at a time. When does it stop being a heap? If there's no precise moment where the change occurs, then does the heap ever truly exist? This is the Sorites Paradox, a deceptively simple dilemma that exposes the fundamental ambiguity in how we categorize the world. It is a paradox of vagueness, a fracture in our understanding of boundaries, numbers, and definitions. It applies to far more than just heaps of sand, stretching into identity, morality, and even reality itself. At its core, the paradox reveals the problem of continuum, where one state gradually transforms into another without a clear dividing line. Imagine a person slowly going bald. If one hair is lost, they are not bald. If two, still not. But at some point, they are undeniably bald. The same problem arises when defining old age, wealth, intelligence, or even consciousness. When does a child become an adult? When does a developing mind become self-aware? How many molecules can you remove from a chair before it ceases to be a chair? If no single moment or change is definitive, then do these categories have any real meaning? The origins of the Sorites Paradox trace back to the ancient Greek philosopher Eubulides, who crafted it to challenge the assumptions behind logic and language. In the strictest sense, logic demands clear distinctions. Something is either true or false, X or not X. But the paradox shows that reality often refuses to obey such rigid classification. Categories that feel precise break down under scrutiny, revealing their inherent fuzziness. Philosophers and logicians have attempted to resolve the paradox in multiple ways. One approach is to accept that categories like heap or bald are inherently vague. This leads to the study of fuzzy logic, a system where truth exists on a spectrum rather than in binary terms. Instead of saying someone is bald or not bald, fuzzy logic assigns a degree of baldness, a percentage rather than a yes or no answer. This mirrors how humans naturally perceive things, yet it still doesn't answer the deeper question, where do we draw the line, and does such a line truly exist? Another attempt at resolution involves rejecting the idea that precise definitions are necessary at all. Some argue that just because we cannot pinpoint an exact boundary does not mean the concept is meaningless. A heap of sand still exists, even if its definition is flexible. But this raises another unsettling problem. If boundaries are arbitrary, then how can we justify any classification? If we accept this vagueness in everyday language, does it also apply to ethics, identity, and truth itself? Consider morality. If one small, unethical act is insignificant, then so is the next, and the next. But where does minor wrongdoing cross the threshold into full-scale corruption? The same logic applies to personal identity. You are not the same person you were 10 years ago. Your thoughts, experiences, and even the molecules in your body have changed. But at no single moment did you cease to exist and become someone else. If personal identity is as vague as a heap of sand, then what truly defines the self? The Sorites Paradox does not just expose the limitations of language, it calls into question the very way we construct reality. If our understanding of existence relies on boundaries that do not actually exist, then how stable is our perception of the world? It suggests that much of what we take for granted, concepts, identities, truths, may be built upon foundations that are inherently undefined. So, does a heap of sand exist? Is there such a thing as baldness? Are we the same person we were yesterday? The Sorites Paradox refuses to provide an answer. Instead, it forces us to confront the unsettling possibility that reality is not as neatly divided as we like to believe. And if so much of what we assume to be real is built upon arbitrary distinctions, what else in our world is nothing more than an illusion of certainty? Russell's paradox. There are some things that follow rules so perfectly that they collapse under their own logic. Mathematics, the realm of precision and certainty, seems immune to contradiction until it isn't. Deep within the foundations of set theory, where numbers and objects are categorized with absolute rigor, a single question tears through logic itself. If a set is defined as the collection of things that fit a particular rule, can a set contain itself? And if not, what happens when we try to define a set of all sets that do not contain themselves? This is Russell's paradox, a devastating logical contradiction discovered by British philosopher and mathematician Bertrand Russell in 1901. It is simple to state yet destructive in its implications, exposing cracks in the very foundation of mathematics. To understand the problem, consider a collection of books. A library contains books about various topics: history, science, philosophy. But imagine a new category: books that reference themselves. A book titled The Complete History of This Book belongs in this category because it describes itself. But a book about physics does not reference itself, so it belongs to a different category: books that do not reference themselves. Now apply this logic to sets. A set is just a collection of objects, defined by some common property. There are sets of numbers, sets of shapes, even sets of sets. But what happens if we try to define a new set, the set of all sets that do not contain themselves? Let's call it R. Now the paradox unfolds. Does R contain itself? If it does, then by definition, it should not be in the set, since R is only supposed to include sets that do not contain themselves. But if R does not contain itself, then by its own rule, it should be included in the set. It is both inside and outside itself at the same time. Logic collapses. The contradiction is unavoidable. Russell's discovery sent shockwaves through the world of mathematics and philosophy. The paradox revealed that set theory, the system designed to categorize everything with absolute precision, contained a fatal flaw. If sets could be defined without restriction, contradictions could arise that destroyed consistency. Mathematics, the supposed bastion of truth, was suddenly a house of cards built on unstable ground. This paradox was more than a curiosity. It threatened the foundations of logic itself. Mathematicians had relied on set theory as the bedrock of their discipline, and now that bedrock was crumbling. If sets could generate contradictions, how could mathematics ever be trusted? Russell's paradox forced an urgent re-evaluation of mathematical foundations. Some sought to eliminate paradoxes by imposing stricter rules on set formation, leading to formal systems like Zermelo-Fraenkel set theory, which restricted how sets could be defined. Others attempted to redefine logic itself, introducing hierarchical structures that prevented self-referential loops. The paradox even influenced Gödel's incompleteness theorems, which later proved that any sufficiently complex mathematical system will always contain true statements that cannot be proven within the system, another profound limitation on absolute certainty. Beyond mathematics, the paradox raises unsettling questions about language, self-reference, and the limits of human understanding. If logic itself can create loops that break reality, what other paradoxes might lurk beneath the surface of what we consider rational thought? The paradox of self-reference extends beyond math into philosophy, psychology, and even artificial intelligence. Can a system fully define itself, or does every attempt to categorize the world inevitably lead to contradictions? Russell's paradox is not just an anomaly, it is a warning. It reveals that even in our most precise, carefully constructed systems, contradictions may lurk beneath the surface, waiting to tear everything apart. And if the very foundation of logic can contain a paradox, what does that say about our ability to truly understand reality? The observer's paradox. Reality is not a passive landscape waiting to be observed. It shifts, adapts, and distorts the moment we turn our attention to it. Observation, something we take for granted as a neutral act, is anything but passive. The very fact of watching something can change its behavior, altering the outcome in ways that defy intuition. This is the observer's paradox, a phenomenon that appears in fields as different as physics, psychology, and even sociology, revealing the unsettling truth that pure objective observation may be impossible. At its core, the paradox is simple. When we attempt to study a system, the act of observing it can interfere with its natural state, making it impossible to measure what would have happened had we not been watching. It's as if the universe refuses to let us peek behind the curtain without rewriting the script as we do. One of the most famous manifestations of this paradox comes from quantum mechanics, where the fundamental nature of reality itself seems to depend on observation. Consider the double-slit experiment, one of the strangest and most unsettling results in modern physics. In this experiment, a beam of particles, such as electrons or photons, is fired at a barrier with two slits. If we do not observe which slit each particle passes through, they behave like waves, creating an interference pattern on a screen behind the slits. But the moment we try to measure which slit a particle travels through, the wave-like behavior collapses and the particles act like solid objects instead. In other words, the mere fact that we attempt to observe the path of a particle forces it to behave differently than if it were left unobserved. The question then arises, does reality exist in a definitive state before we observe it, or does our observation bring it into being? The deeper physicists probe, the more unsettling the implications become. Quantum mechanics suggests that observation is not just a passive act, but an active force, collapsing possibilities into singular outcomes. But the observer's paradox is not limited to physics. It also appears in human behavior. In sociology and psychology, this effect is known as the Hawthorne effect. People change their behavior when they know they are being watched. Early experiments at the Western Electric Hawthorne Works in the 1920s found that factory workers' productivity increased not because of changes in working conditions, but simply because they were aware they were being studied. The presence of an observer altered their natural state, making it impossible to determine how they would act under normal circumstances. This effect extends to nearly every domain of human life. Surveillance alters the way people behave in public spaces. Political polling can shift election results simply by influencing how people think about the race. Even in personal interactions, being watched changes our decisions, speech, and even self-perception. We do not merely exist, we perform under the gaze of others. At its deepest level, the observer's paradox forces us to question whether true objectivity is ever possible. If reality shifts when we observe it, can we ever know what the world is like when we aren't looking? The paradox extends to philosophy, particularly in discussions of consciousness and self-awareness. If every thought we have about ourselves influences our perception of who we are, can we ever truly know ourselves in an unfiltered way? Or are we, like the quantum particles in the double-slit experiment, in a constant state of transformation simply because we are aware of ourselves? This paradox challenges the very nature of knowledge. Scientific inquiry assumes that we can study the universe without interfering with it, yet time and time again we find that the act of observation is inextricable from what is observed. The closer we look, the more we distort what we are trying to understand. Perhaps this paradox is a fundamental feature of reality itself. Maybe the universe does not have a fixed state, but instead shifts and adapts in response to the conscious entities that try to measure it. If that is true, then the search for objective truth may forever be limited by the very minds that seek it. The unexpected lottery paradox. A lottery ticket is worthless. The odds of winning are so infinitesimally small that no rational person should ever expect to win. And yet someone does. Someone always does. The unexpected lottery paradox forces us to confront a contradiction at the heart of probability, logic, and belief. If an event is so unlikely that we have no reason to expect it, how do we make sense of the fact that it still happens? At its core, the paradox is simple. Imagine a massive lottery, one where millions or even billions of people participate. The chance of any single individual winning is so small that it is rational to believe that no one will win. If we apply this reasoning to every single ticket, we conclude that the lottery will have no winner at all. And yet, when the numbers are drawn, a winning ticket emerges. This creates an apparent contradiction. We were logically justified in believing that no one would win, and yet we were inevitably proven wrong. This paradox is closely related to the problem of probabilistic reasoning, where extremely low probabilities lead to seemingly absurd conclusions. Consider another version of the paradox. A fair coin is flipped 1,000,000 times. The probability that it will land on heads every single time is so close to zero that we would never expect it to happen. And yet there is nothing physically preventing this outcome. If we repeated the experiment an astronomical number of times, a sequence of 1,000,000 heads would eventually occur. The paradox is not in the result itself, but in the tension between expectation and reality, between what we believe to be impossible and what is merely improbable. This problem extends beyond gambling and probability theory. It manifests in real-world decision-making, existential risk, and even cosmology. Consider the origin of life itself. The odds of complex molecules randomly assembling into a self-replicating system may be extraordinarily low, yet life exists. Some argue that this makes life's existence paradoxical. How can something so improbable be real? Others counter that improbable things are inevitable given enough opportunities. In a vast enough universe, even the rarest outcomes must eventually occur. But the paradox also reveals a flaw in human reasoning. We are terrible at intuitively understanding large numbers and small probabilities. People consistently overestimate the likelihood of rare disasters, like plane crashes or shark attacks, while underestimating common risks like heart disease. In contrast, we assume that extremely low probabilities mean something will never happen, even when we know that rare events must occur somewhere sometime. This has unsettling implications for our perception of reality. If an event is so unlikely that we have no reason to believe in it, should we still prepare for it? Should we live as if the highly improbable is, in fact, possible? The paradox suggests that dismissing rare events outright is a mistake, because eventually the impossible happens. Philosophically, this paradox challenges the foundation of inductive reasoning, the idea that we can predict the future based on past experiences. We assume that just because something is unlikely today, it will remain unlikely forever. But as the lottery paradox reminds us, unlikelihood does not mean impossibility. The moment the winning ticket is drawn, the impossible becomes real. So how do we reconcile this paradox? Some argue that we should rethink our expectations. Instead of assuming that highly improbable events will never happen, we should accept that in a world of vast possibilities, the absurd is inevitable. Others take a more practical approach, acknowledging that while rare events do occur, they are not predictable enough to be useful in decision-making. But the tension remains. If logic tells us that the winner of a lottery should not expect to win, how do they explain the ticket in their hands? If the improbable is destined to happen, then what else in our world, what else in our lives, seems impossible today, but will one day be undeniably real? The Twin Paradox. A pair of twins born at the same moment, identical in every way. One stays on Earth, living a normal life. The other boards a spacecraft and hurtles away at near light speed, only to return decades later. When they reunite, something impossible has happened. The twin who stayed on Earth has aged dramatically, while the traveler remains eerily young. Time itself has betrayed intuition, creating a paradox that defies common sense. This is the Twin Paradox, one of the strangest consequences of Einstein's theory of relativity, a problem that stretches our understanding of time, motion, and identity. At first glance, the paradox seems simple. According to special relativity, time slows down for objects in motion relative to a stationary observer. The faster something moves, the slower time passes for it. This means that as the traveling twin accelerates close to the speed of light, they experience time more slowly than their twin on Earth. When they return, decades may have passed for the Earthbound twin, while only a few years have passed for the traveler. But here's where the paradox emerges. From the perspective of the traveling twin, it is the Earth that is moving at high speed, not them. If motion is relative, shouldn't the Earthbound twin also experience time dilation, making the two age at the same rate? The paradox seems to create a contradiction. Both twins should see the other as aging more slowly, which means they should remain the same age when reunited. And yet only one twin is younger. To resolve this, we must understand that the paradox is not truly symmetrical. The key lies in acceleration. The traveling twin does not remain in a single unchanging frame of reference. They accelerate away from Earth, turn around, and accelerate back. In contrast, the twin who stays on Earth remains in an inertial frame, experiencing no dramatic shifts in velocity. The act of turning around breaks the symmetry of the situation. One twin undergoes acceleration and deceleration, while the other does not. Special relativity alone does not fully resolve the paradox, but when combined with general relativity, which describes how acceleration affects time, it becomes clear. Acceleration shifts the traveling twin into a new time path, making their aging process different from that of their stationary sibling. The implications of the twin paradox extend beyond a mere thought experiment. If time can slow down depending on motion, does that mean time is not absolute? The answer, confirmed by experiments with high-speed particles and precise atomic clocks, is yes. Time is not a universal constant. It is elastic, bending and stretching depending on speed and gravity. Astronauts aboard the International Space Station, moving at high velocities relative to Earth, experience time slightly more slowly than those on the planet's surface. Though the difference is tiny, measurable only in fractions of a second, it confirms that time is not fixed. But the paradox forces us to think deeper. If two people can age at different rates depending on motion, what does that mean for our concept of personal identity? If you travel at near light speed, could you return to an Earth where centuries have passed, where everyone you knew is gone? Does time dilation create a kind of one-way time travel, an escape into the future from which there is no return? There is another unsettling aspect to the paradox. If time is flexible, then our everyday understanding of past, present, and future might be an illusion. If motion alters the rate at which time flows, does this mean that time itself is just another dimension like space? Are we all just moving through time at different speeds, unaware of how relative our own existence might be? The twin paradox is not a trick of math, nor an illusion of perception. It is real, tested, and verified. Time does not flow the same for all observers. We like to think of time as something steady, something universal, something fair. But physics suggests otherwise. It whispers that time is fragile, that our experience of it is an illusion shaped by motion and gravity, that the ticking of a clock can betray the very thing it was designed to measure. So the question remains, if time is not absolute, if reality itself bends under the laws of motion, then what does it mean to live in a universe where two people, born in the same moment, might never truly share the same time? The Teletransportation Paradox. You step into a machine, a marvel of technology, a transporter capable of dismantling you atom by atom, recording your entire molecular structure and transmitting the data across space to a distant location. There, using raw matter, the machine reconstructs you, every neuron, every memory, every tiny imperfection in your skin, replicated precisely. You step out, feeling normal, remembering your life exactly as it was before. But was the you that entered the machine truly the same as the one that emerged? Or did the original version of you die, leaving behind only a perfect copy? This is the Teletransportation Paradox, a thought experiment that challenges our deepest intuitions about identity, consciousness, and what it means to exist. If a machine could perfectly copy you, molecule for molecule, and recreate you elsewhere, would you still be you? Or would the original you cease to exist, with only a replica remaining? The paradox begins with a simple question: what defines the self? If identity is purely a matter of physical arrangement, then as long as the copy is identical, it must be the same person. But if identity is tied to an unbroken continuity of experience, then the original dies, and the copy, no matter how perfect, begins a separate existence. Consider a disturbing variation. Instead of disassembling you, the transporter malfunctions. Instead of destroying the original, it simply creates a second version of you at the destination. Now there are two of you. Which one is the real you? If both versions remember stepping into the machine, recall every childhood memory, and share the same thoughts, how can one claim to be more authentic than the other? And yet, standing face to face, each would see the other as an imposter. The problem grows more unsettling when we apply it to everyday life. What if this isn't just a problem for futuristic teleportation, but something that happens all the time? The human body constantly replaces its cells. Most of the atoms in your body are not the same ones you were born with. If identity persists, despite physical change, then what exactly makes you the same person from one moment to the next? If a perfect copy of you exists, and you feel like you are still you, what stops it from being you just as much as the original? Some philosophers propose that consciousness is an illusion of continuity, a trick of the brain that stitches together experiences into a seamless flow. But the teletransportation paradox forces us to question whether this continuity is real or just a comforting narrative. If a machine could perfectly replicate you in an instant, without you ever realizing a transition occurred, would it make any difference? And if it does, if something vital is lost in the copying process, then what exactly is that essence, and where does it go? The paradox also has implications for the future of human existence. If we could upload consciousness into machines, preserving every memory and personality trait, would the uploaded version be truly you or just an imitation? Would you survive the process, or would you die, leaving behind only a ghost in the machine? Some argue that identity is merely pattern continuity, not physical continuity. If a person's consciousness is defined by their thoughts, memories, and behaviors, then as long as those are preserved, identity remains intact. By this logic, teleportation is no different from waking up each morning. The old self ceases to exist, and a new self, indistinguishable from the old, takes its place. But if this is true, then every moment is a kind of teletransportation, with the version of you that exists now being no more connected to the past than a perfect replica would be. So the question lingers: if you step into the machine, knowing you will emerge on the other side in perfect condition, do you trust it? Or do you hesitate, sensing that something indescribable, something beyond atoms and data, might be lost forever? The Sleeping Beauty Paradox. A researcher approaches you with a peculiar experiment. You will be put to sleep on Sunday, and a fair coin will be flipped. If it lands heads, you will be woken up on Monday, and then the experiment ends. If it lands tails, you will be woken up on Monday, put back to sleep, and then woken up again on Tuesday. Each time you wake up, your memory of prior awakenings will be erased. When you wake up, disoriented but aware of the experiment, the researcher asks you one question: what is the probability that the coin landed heads? At first glance, the answer seems obvious. The coin is fair, meaning it has a 50% chance of landing heads and a 50% chance of landing tails. But the moment you wake up, things become far less certain. Given that your memory is wiped between awakenings, you have no way of knowing whether today is Monday or Tuesday. All you know is that you are awake, but how should that influence your probability assessment? This is the Sleeping Beauty Paradox, a deceptively simple probability puzzle that fractures logical intuition. The core question is, does the mere fact of waking up change the way probabilities should be assigned? Two camps, known as halfers and thirders, have battled over the answer for years, each believing the other is making a fundamental mistake. The halfer argument is straightforward. Before the experiment, Sleeping Beauty knows the coin has a 50% chance of landing heads and a 50% chance of landing tails. Since waking up doesn't change any fundamental information about the fairness of the coin, the probability of heads remains 50%. In other words, the number of awakenings shouldn't affect the original probability. The thirder argument, however, considers a different perspective. If the coin lands heads, you wake up once on Monday. If it lands tails, you wake up twice on Monday and Tuesday. Since each awakening is indistinguishable, and you are equally likely to find yourself in any awakening, there are three possible situations in which you could find yourself. 1. You wake up on Monday after a heads result. 2. You wake up on Monday after a tails result. 3. You wake up on Tuesday after a tails result. Only one out of these three situations corresponds to the coin landing heads. Since you must be in one of these three scenarios, but cannot tell which, the probability of heads upon waking is 1/3, or roughly 33%, rather than 50%. This reasoning hinges on the fact that the number of times you wake up is directly tied to the coin flip's outcome. Since waking up twice is twice as likely in the tails case, the probability should reflect this bias. The paradox challenges how probability should be assigned when events depend on subjective experience, on how many times an observer exists rather than just raw chances. The Sleeping Beauty Paradox isn't just an abstract thought experiment. It raises fundamental questions about how probabilities should be interpreted in real-world scenarios. Some theorists link it to the anthropic principle, the idea that our own existence should influence how we assess probabilities about the universe. If we are part of an experiment where some realities contain more versions of us than others, should we consider our presence as evidence weighting the odds? The paradox also has implications for quantum mechanics. In the many-worlds interpretation, every quantum event spawns multiple universes, each representing a different outcome. If reality splits into different branches with varying numbers of observers, should probabilities shift accordingly? Could Sleeping Beauty's experience serve as an analogy for our own place in the multiverse? But perhaps the most unsettling part of the paradox is its challenge to how we perceive certainty. In everyday life, we rely on probabilities to make decisions, assuming that new evidence updates our beliefs in a predictable way. Yet here, even when no new information is introduced, the very act of being conscious forces a reassessment of reality. So when you wake up in the experiment, staring at the ceiling with no memory of whether this is the first or second awakening, ask yourself, are you living in a world where heads was flipped, or are you simply more likely to exist in a world where tails created more versions of you? And if the nature of probability itself depends on the observer, what does that mean for every waking moment of your own life? The Infinite Hotel Paradox. A weary traveler arrives at a hotel after a long journey, hoping to secure a room for the night. The receptionist, a well-dressed man with an unnervingly calm demeanor, greets him with an apologetic smile. "I'm terribly sorry," he says, "but we are completely full." The traveler looks up at the sign above the entrance. Hilbert's Grand Hotel, infinite rooms, infinite guests. How can a hotel with an infinite number of rooms be full? And more importantly, if every room is occupied, why does the receptionist's smile suggest there's still a way in? This is the Infinite Hotel Paradox, a mind-bending thought experiment devised by mathematician David Hilbert. It forces us to grapple with the bizarre nature of infinity, a concept that refuses to obey the logic of finite numbers. At first glance, a hotel with infinite rooms seems like it should never be full. But suppose every single room is occupied. If a new guest arrives, it appears as though there is simply no space left. Yet Hilbert's receptionist offers a solution. "Not to worry," he says. "I'll simply shift every guest one room over. The person in room 1 will move to room 2, the guest in room 2 will move to room 3, and so on. Since there's no last room, we can keep shifting forever. Room 1 is now vacant, and the traveler is free to check in." A hotel that is both full and able to accommodate more guests defies intuition, but this is the paradox of infinity. There is always room for more. But the real strangeness begins when larger groups arrive. Suppose an infinite number of travelers show up, each hoping for a room. The receptionist barely bats an eye. "Simple," he says. "Every guest will move to a room number that is twice their current number. The guest in room 1 moves to room 2, the guest in room 2 moves to room 4, room 3 moves to room 6, and so on. Now all odd-numbered rooms, an infinite set of them, are free, and the infinite new guests are assigned to those rooms. The hotel was already full, yet it still managed to fit an entirely new infinity of guests inside." If this sounds impossible, that's because it is, at least in the world of finite numbers. In our everyday experience, a full parking lot means no more cars can enter. A full restaurant means no more diners can be seated. But infinity doesn't work like that. Infinity is not a number, but a concept, and one that allows for counterintuitive results. The paradox only deepens from here. Suppose every guest in the hotel suddenly checks out, leaving all rooms empty. How many guests remain? The intuitive answer is 0, but infinity doesn't behave so predictably. Depending on how you count, the number of remaining guests can still be infinite, or paradoxically, it can be less than infinity but more than 0. Infinity bends the very notion of quantity. This paradox isn't just a mathematical curiosity, it has profound implications for how we understand the universe. Cosmologists have debated whether the universe itself is infinite. If it is, then questions about size, duplication, and possibility become as strange as Hilbert's hotel. If the universe is infinite, then there are an infinite number of versions of you existing in different variations of reality. If time is infinite, then does anything truly begin or end? The infinite hotel paradox also appears in probability and logic. If an infinite universe contains an infinite number of events, then every possibility, no matter how unlikely, must happen somewhere. There is a version of you that has lived an identical life up until this moment, but just decided to stand up and walk away. There is a version of Earth where the laws of physics are slightly different, making light bend in ways we can't comprehend. In an infinite system, the impossible becomes inevitable. Yet, the paradox also serves as a warning. Infinity is not just a playground for strange thought experiments. It challenges how we define reality itself. If infinity can accommodate more guests without ever truly being full, then what does full even mean? If an infinite universe contains all possibilities, then what does possible mean? As the traveler settles into his newly vacated room, he wonders about the absurdity of it all. The hotel was full, but not really. More guests arrived, but it still wasn't full. An infinite number left, yet infinity remained. The receptionist hands him a key with an amused look. "Infinity is funny like that," he says. "Would you like to extend your stay indefinitely?" The measure problem in cosmology. In an infinite universe, what does it mean to say that something is more likely than something else? If there are infinite galaxies, infinite Earth-like planets, and infinite versions of you watching or listening to this right now, then how do we even begin to talk about probabilities? The measure problem in cosmology is a paradox that arises when trying to assign meaningful probabilities in a universe that may have no limits. At first glance, probability seems straightforward. If you flip a fair coin, the odds of landing on heads or tails are 50-50. If you roll a six-sided die, each number has a 1 in 6 chance of appearing. But when dealing with infinity, probabilities lose their meaning. How do you measure how often something happens when there are infinite copies of everything happening? Imagine a vast multiverse where new universes are constantly being created. Some of these universes might resemble our own, while others may have wildly different physics, stars that burn cold, planets that never form, life that evolves in ways beyond comprehension. Suppose we ask a simple question: what fraction of all universes contain intelligent life? To answer, we need to count the number of universes with life and compare it to the number without. But if both numbers are infinite, the ratio becomes meaningless. Infinity divided by infinity doesn't give a well-defined number. It is an unsolvable mathematical expression, an undefined quantity. Even if there are vastly more lifeless universes than living ones, in an infinite system, everything occurs infinitely many times, making any fraction ambiguous. The problem worsens when we try to predict the future of our own universe. Many cosmological theories suggest that space is constantly expanding, with quantum fluctuations giving rise to new regions, each potentially evolving into its own separate universe. This is known as eternal inflation, and it suggests that new universes are born infinitely often. If universes are being produced at different rates in different places, how do we determine which outcomes are common and which are rare? Physicists often try to solve this by introducing a measure, a mathematical way to compare infinities and assign meaningful probabilities. But every method of measuring infinity leads to contradictions. Some measures suggest we are overwhelmingly likely to be in a young, chaotic universe rather than a stable one. Others imply that our observations of dark energy, the mysterious force driving cosmic expansion, are highly improbable. One of the most unsettling consequences of the measure problem is that it may undermine the anthropic principle, the idea that the universe appears fine-tuned for life because we are here to observe it. If an infinite number of universes exist, then every possible version of reality occurs somewhere, including ones where life emerges purely by chance, with no fine-tuning required. If so, does our universe really need to be special, or is it just one of infinite possibilities with no deeper significance? Some physicists have proposed cutoff methods, artificial limits placed on infinite systems to make probabilities manageable, but these cutoffs are arbitrary. Imagine trying to count how many even numbers exist. If you stop at 1,000, there are 500. If you stop at 1,000,000, there are 500,000. But in reality, the set of even numbers is infinite, just like the set of odd numbers. Any cutoff distorts reality rather than truly solving the problem. Other solutions suggest that our understanding of probability itself may be flawed. Perhaps, in an infinite universe, we need to rethink what it means to say that one thing is more likely than another. Maybe our intuition, shaped by a world of finite numbers, simply cannot grasp the nature of an infinite cosmos. The measure problem forces us to confront uncomfortable truths about the nature of existence. If our universe is just one among infinite possibilities, what does that say about our place in it? If everything that can happen does happen somewhere, then what distinguishes our reality from any other? Are we truly experiencing the universe, or just a universe among countless others, with no special significance? Perhaps the most disturbing implication is that, without a well-defined measure, all predictions about the future of the universe become meaningless. If we cannot assign probabilities in an infinite system, then science itself, at least in the realm of cosmology, may run into fundamental limitations. If every possibility is realized infinitely many times, then anything that can happen has already happened, is happening now, and will happen again, somewhere. And if that's the case, then what does likely even mean anymore? The two envelopes paradox. You sit at a table, staring at two identical envelopes. Inside each one is a sum of money, but you don't know how much. You're told that one envelope contains exactly twice as much as the other. You can pick one at random, open it, and decide whether to keep it or switch to the other envelope. Seems simple enough, until you start thinking about it. You reach for an envelope and open it. Inside you find $100. Now comes the choice. Do you keep it or switch? At first glance, the odds seem perfectly even. The other envelope could either hold $50 or $200. But here's where the paradox takes hold. Your mind starts running the numbers, and something feels off. If the other envelope holds $200, switching would double your money. If it holds $50, switching would cut your money in half. Since you originally had an equal chance of picking either envelope, you reason that there's a 50% chance of each outcome. Now you try to calculate your expected winnings. If you switch, you could either gain $100 or lose $50, but when you average the two possibilities, you find that the expected value of switching is $125. Wait, if switching always increases your expected payout, then logically, you should switch. But the strange part is that this logic applies no matter what's inside your first envelope. If you had picked the other one first, the exact same reasoning would convince you to switch back. This creates an infinite loop of doubt. You should switch, but then you should switch again and again forever. How is this possible? The paradox arises from the way probability and expectation are being used. When you opened the envelope, you assigned equal probabilities to the other envelope containing either half or double the amount. But that assumption only makes sense before you see the number inside. Once you've opened it, the total amounts aren't random. They were already chosen by a hidden rule that you don't know. The mistake is treating your revealed number as if it were randomly assigned, when in reality, it was already determined by the setup of the game. Another way to resolve the paradox is to realize that it depends on an infinite scale of money. If there's no upper limit to how much money the envelopes could contain, then yes, switching always seems to make sense. But in reality, money isn't assigned infinitely. There has to be some rule about how the amounts were chosen in the first place. Without knowing that rule, the probabilities become meaningless. Some mathematicians argue that the paradox is an illusion, a trick of how we frame the problem. The way we set up the expectation calculation leads to an answer that feels logical but is actually misleading. Others suggest that the paradox reveals a deeper issue with our intuitive understanding of probability, especially when it comes to decisions where relative values obscure absolute ones. But maybe the most unsettling answer is that there isn't a rational way out. The paradox traps you in an endless cycle where every logical step leads you back to the same uncertainty. No matter what you do, you can't shake the feeling that you've made the wrong choice. So, do you switch or stay? The paradox doesn't just question probability, it forces you to confront the limits of rational decision-making itself. Causal loop paradoxes. A man walks into a bookstore and finds an old, dusty manuscript on the top shelf. As he flips through its pages, he realizes it contains detailed instructions for building a time machine. He spends years deciphering the text, constructing the machine, and eventually traveling back in time. Upon arrival, he feels an inexplicable urge to leave the very same manuscript in the bookstore, where decades later his past self will find it. But who wrote the manuscript? It was never actually created by anyone. It simply exists, looping through time without an origin. This is a causal loop paradox, a situation where an event is trapped in a circular cause and effect chain with no discernible beginning. A person, an object, or even knowledge itself can become stuck in time, existing purely because it was always meant to. Imagine a scientist receives blueprints for an advanced technology from a visitor claiming to be from the future. The scientist builds the device, and years later, he sends the same blueprints back in time to his younger self. The knowledge has no point of origin. It simply exists within the loop. Did the scientist invent the technology, or did it invent itself? The problem with causal loops is that they defy the fundamental nature of cause and effect. Normally, things happen in a sequence. A leads to B, and B leads to C. But in a causal loop, the sequence folds in on itself, creating a timeline that is self-sustaining but logically incomplete. It challenges the very idea that events need a beginning. One of the most famous examples is the Predestination Paradox, a version of the causal loop where someone tries to change the past only to inadvertently cause the event they were trying to prevent. A time traveler goes back to warn a scientist about a disaster, hoping to prevent it. But in the process, the warning triggers the exact chain of events that lead to the catastrophe. Instead of breaking the cycle, they unknowingly become part of the loop. There's also the ontological paradox, which applies to objects and information that seemingly appear out of nowhere. A musician in the present learns a beautiful song from an old recording. Years later, he plays it for a young listener, who records it and later becomes the famous musician whose song was recorded in the first place. The song has no true creator. It exists in a loop, forever passing itself through time. Some physicists argue that causal loops aren't entirely impossible. The laws of physics, particularly within general relativity, don't outright forbid time loops, though they remain purely theoretical. If such loops existed, they could allow for self-contained histories where certain events just happen without ever being caused by anything outside the loop. Others suggest that paradoxes like these imply that time travel cannot work in the way we imagine, that some mechanism, whether it's the nature of reality itself or some unknown law of physics, must prevent causal loops from forming. After all, if the universe allowed information, objects, or people to appear without an origin, wouldn't that violate everything we understand about the conservation of matter and the progression of time? But the unsettling possibility remains. What if some things don't need an origin? What if reality allows for events that exist simply because they must? A notebook filled with knowledge, a song that writes itself, a time traveler who shapes his own past. Causal loops challenge our deepest assumptions about what it means for something to exist at all. The quantum Zeno effect. A physicist prepares a delicate quantum experiment, setting up an unstable particle expected to decay within a few seconds. But something strange happens. The more frequently the particle is observed, the less likely it is to decay. It lingers in its original state, as if the act of watching it is freezing it in time. The phenomenon at play here is the quantum Zeno effect, a paradox of quantum mechanics that suggests constant observation can prevent change from happening. Named after Zeno of Ela, the ancient philosopher who proposed paradoxes about motion and progress, this effect challenges our understanding of cause, effect, and the role of observation in shaping reality. To understand the strangeness of this effect, consider a simple analogy. Imagine a candle burning down, its wax melting slowly as the flame consumes it. Now picture a scenario where every time you glance at it, the candle immediately resets to its original height. As long as you keep looking at it frequently enough, it never burns down. But the moment you stop watching, it continues as if nothing had happened. In this paradoxical scenario, your observation halts the passage of time for the candle. This is eerily similar to what happens at the quantum level. In quantum mechanics, particles do not behave like classical objects that move through space in predictable ways. Instead, they exist in superpositions, meaning they occupy multiple possible states simultaneously. However, the moment you observe a quantum system, its wave function collapses, forcing it into a single state. If you observe it over and over again at the right intervals, you can prevent it from transitioning to a different state, effectively trapping it in place. This means that the very act of measurement dictates whether a particle changes or remains unchanged. This isn't just a strange thought experiment. The quantum Zeno effect has been confirmed in real-world experiments. Scientists have observed that certain particles, when measured rapidly enough, appear to freeze in their initial state, defying expectations about how they should evolve over time. Physicists have conducted tests using atoms, photons, and superconducting qubits, finding that repeated observation prevents their natural decay. This suggests that measurement isn't just a way to passively gather information about a system, it actively alters the system's evolution. But the implications of the quantum Zeno effect stretch far beyond atomic particles. It raises unsettling questions about the nature of time, consciousness, and reality itself. If observing something over and over again can prevent change, then is time truly flowing continuously, or is it only real when measured? What if, at some fundamental level, time is not an independent force, but something tied directly to observation? This idea touches on an even deeper mystery. If all things require measurement to truly change, then what was time doing before conscious observers existed to measure it? Even more unsettling is the idea that the quantum Zeno effect could, in theory, be applied to biological systems. If rapid observation can stop atomic decay, could it also, under extreme conditions, halt the processes responsible for aging or even death? Some physicists have speculated, half-jokingly, that a perfectly aware consciousness, one that is somehow observing itself in an unbroken loop, could exist in a kind of frozen state, untouched by the natural flow of time. This idea mirrors certain concepts in Eastern philosophy, which suggest that reality is shaped by awareness and that observation itself is a force. This paradox also connects to a broader mystery in quantum physics known as the measurement problem, the unresolved question of why the act of measuring a quantum system forces it into a definite state. If observation truly plays a fundamental role in shaping the behavior of particles, then what does this imply about the universe itself? Could the reality we experience be a kind of vast quantum system, one that only solidifies when observed? Some interpretations of quantum mechanics, such as the participatory universe model proposed by physicist John Wheeler, suggest that reality might not exist in a definite form until it is perceived. There is also the possibility that the quantum Zeno effect hints at a deep connection between time and consciousness. If time slows or halts under continuous observation, could our perception of time be shaping reality itself? Neuroscientists have observed that during moments of heightened awareness, such as in life-threatening situations, people report time seeming to stretch or slow down. While this is usually explained as a function of the brain processing information more rapidly, could it also be a macro-level reflection of a quantum phenomenon? In the end, the quantum Zeno effect is not just a bizarre trick of physics, it is an open doorway to some of the most profound questions about existence. It suggests that change itself may not be an inherent feature of reality, but something that depends on interaction, perception, and awareness. It forces us to consider whether we are passive observers in a universe unfolding independently of us, or whether we play a much more active role in determining the fate of reality itself. Does time flow continuously, or does it only move forward when we stop looking? And if observing reality prevents it from changing, then what happens to a universe that is never observed at all? The Monty Paradox, a brightly lit game show stage. 3 closed doors. Behind one, a brand new car. Behind the others, nothing but worthless goats. The host, grinning, asks you to make a choice. You point to a door number 1. But before revealing what's behind it, the host does something unexpected. He opens another door, revealing a goat, and then offers you a chance to switch to the remaining unopened door. It seems like a 50-50 choice now, doesn't it? Does it really matter whether you switch or stay? Welcome to the Monty Paradox, one of the most famous and counterintuitive puzzles in probability. Named after Monty Hall, the host of the classic game show Let's Make a Deal, this paradox challenges our natural instincts about probability, revealing just how unreliable our intuition can be when faced with uncertainty. At first glance, it seems as though staying or switching should make no difference. There are 2 doors left, and one has the car, so shouldn't the odds be equal? But the math tells a different story. Let's go back to the beginning. When you first pick a door, you have a 1 in 3 chance of picking the car, and a 2 in 3 chance of picking a goat. If you happen to choose the car, then switching would make you lose. But if you originally picked a goat, switching would win you the car. And here's the crucial realization. Since you had a 2/3 chance of picking a goat, that means you have a 2/3 chance of winning if you switch. Still, many people refuse to believe this, convinced that their gut feeling telling them that it's a 50-50 shot must be right. Even professional mathematicians have been known to resist the solution at first. The paradox became widely known after being popularized by Marilyn Vos Savant in the 1990s, when thousands of readers wrote angry letters insisting that switching couldn't possibly improve the odds. But they were wrong. The easiest way to see why switching is the better choice is to imagine the game played on a much larger scale. Suppose there are not 3 doors, but 100. You pick one door at random, meaning you have only a 1% chance of choosing the car. That means there is a 99% chance that the car is behind one of the other doors. Now, Monty Hall, who always knows what's behind each door, reveals 98 goats, leaving just 1 remaining unopened door. Would you switch now? Of course, because almost all of the losing options have been eliminated, and it was overwhelmingly likely that you originally picked wrong. The logic is the same with 3 doors, just harder to see. But why does the Monty Paradox feel so deceptive? The problem lies in the way our minds interpret probability. Humans naturally assume that new information resets our chances rather than shifting the existing probabilities. In this case, the crucial detail is that Monty is not opening a random door. He is opening a door knowing it does not contain the car. This controlled elimination of possibilities is what makes switching the superior choice. This paradox extends beyond game shows and probability puzzles. It reflects a much deeper flaw in human reasoning. Our instincts often struggle to properly account for conditional probabilities, leading us to make irrational decisions in everything from gambling to medical diagnoses. In real life, we frequently assume that 2 options are equal when, in fact, hidden factors skew the odds dramatically. The Monty Paradox also ties into a broader theme in decision-making, our resistance to change. Even when presented with logical proof that switching is the right move, many people still hesitate. The emotional attachment to an initial choice, the fear of regret, or simply the unwillingness to accept that our intuition is flawed can all lead us to stick with a losing decision. In the end, the Monty Paradox is not just about doors, goats, or game shows. It is about how we perceive probability, how we resist counterintuitive truths, and how deeply flawed our reasoning can be in the face of uncertainty. It teaches us that the right decision often feels wrong, and that sometimes the best way to win is to let go of what we thought we knew. So the next time life offers you a second chance, ask yourself, is this just a meaningless choice, or are the odds shifting in my favor? The absent-minded driver paradox. A lone driver speeds down a dark highway, his thoughts drifting like the road signs flickering past. He knows his destination, a fork in the road where a critical choice must be made. One path leads home, the other leads into the unknown. But there's a problem. The driver is absent-minded. By the time he reaches the fork, he might forget where he is, and worse, he might not even remember that a choice was necessary. This is the absent-minded driver paradox, a strange riddle that challenges logic, probability, and the very nature of decision-making itself. It begins with a simple setup. Imagine a driver who must navigate a highway with one major split. Before setting off, he knows the rules. If he chooses correctly, he reaches his goal. If he chooses wrong, he's trapped in a loop, forced to drive endlessly. At the start of his journey, he can think through the probabilities, calculate his chances, and plan his choices. But once he's driving, things change. He's forgetful. The moment he arrives at the fork, he doesn't remember whether it's the first time he's encountered it or if he has already taken the wrong turn before. His past decisions are erased from his memory, leaving him with nothing but the present moment and a 50-50 guess. The paradox lies in this disconnect. He starts his journey with perfect reasoning, yet once he reaches the crucial moment, that reasoning collapses into randomness. He can know the right move in theory, but never reliably act on it in practice. His decision becomes a gamble, even though it was supposed to be a calculated choice. Mathematicians and philosophers have wrestled with this paradox, trying to determine what the driver should rationally do. At the start of the journey, probability suggests he should take the correct exit the first time he encounters the fork. But because he won't remember if he's already made a mistake, he will always feel as though he's encountering the fork for the first time, making each decision seem equally uncertain. This breakdown of logic into chance is what makes the paradox so unsettling. It reveals how the limits of memory and perception can override pure reason. At its core, the absent-minded driver paradox exposes a deep flaw in the way we think about rational decision-making. In theory, choices should be made based on the best available information. But what happens when we don't know whether we're experiencing something for the first time or repeating an error? In life, we often believe we are making fresh decisions, unaware that we might be retracing our own mistakes. This paradox extends beyond a simple thought experiment. It echoes into real-world dilemmas, from economic decisions to moral choices. How often do we assume we're acting wisely, only to be caught in cycles of repeated errors? How often do we believe we are in control, only to find ourselves at the mercy of forgotten choices? The driver continues down the road, unaware if this fork is new or if he has already passed it once before. He hesitates, grips the wheel, and makes a decision. Whether it leads him home or back into the loop, he will never know. The free will paradox. You stand at a crossroads, staring at two diverging paths, left or right. The decision feels entirely your own, as if, at this very moment, you could freely choose either direction. But could you? What if, from the moment of your birth, the neurons in your brain, the laws of physics, and the chain of cause and effect have already determined exactly which path you'll take? This is the free will paradox, a riddle that lies at the heart of human existence. Are we truly in control of our choices, or are we merely acting out a script written by forces beyond our understanding? The paradox emerges when we attempt to reconcile two seemingly contradictory truths. We feel as though we make free choices, yet every choice we make appears to be the inevitable result of prior events. If we assume that the universe operates under determinism, then every action, every thought, every hesitation, every decision can be traced back to an unbroken chain of causes stretching back to the beginning of time. The motion of the planets, the firing of neurons, the outcomes of history, all of it unfolds like a massive domino effect. If that's true, then free will is an illusion. You could no more choose differently than a falling rock could decide to stop midair. But if we reject determinism and claim that our choices are truly free, we run into another problem. If a decision is not caused by anything prior, if it emerges from nowhere unbound by past events, then isn't it just randomness, a roll of the cosmic dice? And if decisions arise purely from chance, can they be considered choices at all? A random process is not the same as a willful decision. This is where the paradox takes hold. If our actions are caused, we are not free. If they are not caused, they are meaningless. No matter which way we turn, true free will seems to slip through our fingers. Some have attempted to escape the paradox by redefining free will. One argument claims that as long as our decisions align with our desires and reasoning, we can consider them free, even if those desires themselves were determined by prior causes. Others turn to compatibilism, the idea that free will and determinism are not in conflict, but instead describe different aspects of the same reality. Under this view, your choices are determined, but because they are shaped by your own mind and reasoning, they still belong to you. Quantum mechanics adds another layer of complexity. Unlike classical physics, where everything follows strict causal rules, quantum theory introduces an element of uncertainty. Some have speculated that this randomness could create a loophole for free will, but randomness alone does not create meaningful choice. The problem remains unsolved. And so, we are left in a strange place. We feel like conscious agents, actively deciding our fate. But the paradox whispers otherwise. If we are bound by causality, then every word, every movement, every belief was always inevitable. If we are free, then our choices must somehow escape the web of cause and effect, yet without descending into chaos. So, did you freely choose to listen to this? Or was it always going to happen? Maybe the choice was never really yours to begin with. The paradox of the Criterion. How do you know what you know? It seems like a simple question at first. You rely on reason, evidence, or experience. But how do you know those sources are reliable? What standard are you using to separate truth from illusion, knowledge from deception? And more importantly, how do you justify that standard itself? This is the paradox of the Criterion, a problem that cuts to the core of epistemology, the study of knowledge itself. It challenges our ability to determine truth by revealing a circular trap. In order to judge whether something is true, we need a reliable method. But in order to know if the method is reliable, we first need a way to verify it. And to verify that verification, we need yet another standard, which also needs to be justified. The cycle never ends. Consider a simple example. Suppose you claim that you can trust your senses because they consistently provide information about the world. But how do you know that consistency proves reliability? Because your reasoning tells you so? But how do you know your reasoning is sound? Because it makes logical sense. But who determines what logic itself is? Every attempt to establish a foundation for knowledge ends up requiring another, deeper foundation, one that itself cannot be independently verified without assuming its validity. The paradox has two major horns, each leading to an unsettling conclusion. On one side, if we require absolute proof for our method of distinguishing truth from falsehood, we are stuck in an infinite regress, demanding justification after justification without ever arriving at a final answer. On the other side, if we do not require proof, if we simply assume that some methods are valid without justification, then we risk basing our entire understanding of reality on an arbitrary, unverified foundation. Either way, certainty remains out of reach. Philosophers throughout history have grappled with this paradox. The skeptics, such as Sextus Empiricus, argued that because no ultimate criterion can be established, we must suspend judgment on all knowledge claims. Others, like Descartes, attempted to escape the trap by proposing a self-evident starting point. His famous cogito, ergo sum, I think therefore I am, as an indubitable foundation. But even this relies on the assumption that existence follows from thought, which itself could be questioned. Some modern thinkers argue that knowledge is more like a web than a hierarchy, with beliefs supporting one another in a coherent system rather than resting on a single ultimate foundation. But even this does not solve the problem. Coherence alone does not guarantee truth. A well-structured delusion is still a delusion. So where does that leave us? Are we forever trapped in an epistemic loop, unable to prove anything beyond doubt? Or do we simply take certain assumptions on faith and move forward despite the uncertainty? The paradox of the Criterion exposes a fault line in human understanding, a reminder that even the most basic knowledge rests on unprovable foundations. And so the question lingers, how do you know what you know, and how do you know that you know it? Newcomb's Paradox. Imagine standing in front of two boxes. One is transparent and contains a crisp $1,000 bill. The other is opaque, its contents unknown. You are given a choice: take only the opaque box or take both boxes. The catch? A highly advanced entity, a superintelligent predictor, has already foreseen your decision. If it predicted that you would take only the opaque box, it placed $1 million inside. But if it predicted that you would take both boxes, it left the opaque one empty. This is Newcomb's Paradox, a thought experiment that seems to pit rational decision-making against itself. No matter how you analyze it, something about it feels contradictory. On one hand, the money is either in the opaque box or it isn't. It was placed there in the past, meaning your choice now shouldn't affect what's inside. But on the other hand, this predictor is infallible. If you take both boxes, you will almost certainly find the opaque one empty. If you take only the opaque box, you will almost certainly find $1 million waiting for you. So, what do? At first, the logic seems clear. If the opaque box already contains money, taking both boxes gets you the most possible cash, $1,001,000 instead of $1 million. But if it's empty, taking both boxes gets you only $1,000 instead of nothing. By that reasoning, you should always take both boxes. This is the approach of causal decision theorists, who argue that your current action can't change the past. The money is already there, or it isn't, so maximizing your outcome means taking both. Yet time and again, those who take only the opaque box walk away $1 million richer. Those who take both leave with only $1,000. This is where evidential decision theory comes in. A different way of thinking about choice. Instead of asking what your action causes, it asks what it suggests. If you won box, it indicates that you're the kind of person who won boxes, meaning the predictor would have seen this in advance and placed the money inside. If you two-box, it suggests that you are a two-boxer, and the predictor likely left the opaque box empty. The paradox hinges on the nature of prediction itself. How can your decision, made in the present, be accurately predicted in the past? If the predictor is truly infallible, is free will even real? And if free will isn't real, does the choice itself even matter? Some attempt to resolve the paradox by arguing that a perfect predictor is impossible. It cannot exist without violating causality, but this doesn't eliminate the tension at the heart of the problem. What if the predictor is just extremely accurate rather than perfect? If it is correct, 99.99999% of the time, the results would be nearly identical. And if that's the case, shouldn't you still one box, knowing that almost everyone who does walks away with a fortune? Others argue that the paradox reveals something deeper about human reasoning. Traditional logic assumes a clean break between past and future, cause and effect. But what if reality doesn't work that way? What if our choices are embedded in a web of causation stretching across time, so that choosing now is part of what determined the past? Newcomb's paradox doesn't just challenge our understanding of decision-making, it forces us to reconsider the very nature of time, causality, and choice. It suggests that even the simplest decisions might not be as free as they seem, that past and future might not be as separate as we assume, and that the act of choosing is in some strange way already written into the fabric of reality itself. So you stand before the two boxes. One is clear, the other mysterious. The choice is yours. Or was it made long before you ever arrived? The Barber Paradox. A small town has a peculiar rule: every man must be clean-shaven. But not everyone shaves themselves. Some rely on the town's one and only barber. This barber follows a strict policy. He shaves all, and only those men who do not shave themselves. It seems like a simple setup, a perfectly logical division of labor. But then comes the question that shatters the whole arrangement. Who shaves the barber? If the barber does not shave himself, then according to his rule, he must shave himself. But if he does shave himself, then by the same rule, he must not shave himself. Either way, the rule contradicts itself. The barber cannot exist under these conditions, yet we started with the assumption that he does. This is the Barber Paradox, formulated by the philosopher and mathematician Bertrand Russell. On the surface, it looks like a quirky word puzzle, but beneath it lies a deep contradiction that exposes one of the most infamous problems in logic: self-reference. The core issue is the barber's rule. It sets up a rigid system that collapses when applied to itself. The paradox arises because the rule attempts to classify people in a binary way. Either you shave yourself or you are shaved by the barber. But when the barber himself is subjected to this rule, it leads to an impossible loop, an unsolvable contradiction. Russell originally devised this paradox as a simplified version of a larger problem in set theory. In mathematics, there was a prevailing idea that sets, collections of objects, could be defined in a straightforward way. But Russell discovered that certain sets, when defined in relation to themselves, break down completely. His most famous example was the paradox of the set of all sets that do not contain themselves. Does this set contain itself or not? If it does, then by definition, it shouldn't. If it doesn't, then it should. Just like the barber, it falls into a loop that logic cannot resolve. This paradox shattered the foundations of mathematical logic at the time. Mathematicians had assumed that any logical system could be built on clean, self-consistent rules, but Russell's discovery proved that even simple rules can lead to contradictions when they reference themselves. The result? An existential crisis for mathematics, one that would lead to sweeping changes in the way logic was understood. One of the most famous responses to paradoxes like this came from Kurt Gödel, whose incompleteness theorem showed that any sufficiently powerful system of logic will always contain true statements that cannot be proven within that system. The Barber Paradox is a small glimpse into that larger, more disturbing truth. Some questions simply cannot be answered within their own rules. But step outside mathematics, and this paradox takes on a strangely familiar shape. We see versions of it in legal systems, bureaucracies, even artificial intelligence. Rules that attempt to define themselves often end up collapsing. Consider a law that states, "This law must be obeyed unless it contradicts itself." If you follow it, you break it. If you ignore it, you follow it. Just like the barber's rule, it self-destructs upon examination. So what happens to the barber? In reality, he simply cannot exist under these conditions. His rule seems reasonable when applied to others, but falls apart when applied to himself. The paradox isn't just about shaving, it's about the danger of absolute, rigid rules in systems that must account for themselves. Perhaps the real lesson of the Barber Paradox isn't about a man with a razor, but about the limits of certainty. Some things, no matter how logical they seem, cannot be neatly classified. And sometimes, the only way to resolve a paradox is to realize that the question itself was impossible to begin with. The Crocodile Paradox. A crocodile lies still on the riverbank, its scales glistening in the sun. In its powerful jaws, it holds a child, snatched from a desperate parent who stands trembling before the beast. The crocodile, with an eerie sense of logic, offers a deal. If you can correctly predict whether I will return your child, I will set them free. If you guess incorrectly, I will keep them. At first, this seems like a cruel but straightforward gamble. Either the parent makes the right prediction, or they do not. But then comes the realization that this is not a fair game at all. What if the parent predicts, "You will not return my child"? Now the crocodile is trapped in a logical paradox. If the prediction is correct, then the crocodile must return the child, but doing so would make the prediction false. If the crocodile keeps the child, then the prediction is confirmed as true, which means the child should have been returned. No matter what the crocodile chooses, it contradicts itself. This is the Crocodile Paradox, an ancient logical puzzle from classical philosophy that exposes the dangers of self-referential conditions. It belongs to a category of paradoxes known as epistemic paradoxes, logical traps that arise when truth and prediction intertwine in impossible ways. At its core, this paradox hinges on a contradiction in conditional reasoning. The crocodile's promise depends on the accuracy of the parent's prediction, but if the prediction itself affects the outcome, the entire structure collapses. The result is a logic loop with no possible resolution. But step back from the riverbank, and the implications of this paradox stretch far beyond the crocodile's twisted game. It mirrors the fundamental instability of self-referential promises, not just in puzzles but in real-world dilemmas. Consider a politician who claims, "I will only keep this promise if you believe I will break it," or a legal contract that states, "This agreement is only valid if you doubt its validity." The same paradox unfolds. A rule that depends on itself creates an infinite contradiction. Even probability cannot escape this paradox. If you had to bet on the crocodile's decision, what odds would you assign? The problem is that there is no stable outcome to measure. Like Schrödinger's cat in quantum mechanics, both alive and dead until observed, the crocodile exists in a logical superposition where no resolution satisfies its own conditions. The paradox also exposes a deeper question about the nature of promises and trust. The crocodile, in some sense, becomes an entity beyond logic, a trickster force that forces us to confront the fragility of certainty. If a promise is contingent on a prediction, and that prediction affects the promise, can any agreement ever be truly reliable? Some interpretations of the paradox suggest a possible escape. The crocodile, being the one who set the rules, can simply choose to act irrationally, breaking logic itself. But this raises a disturbing possibility. What if reality, like the crocodile, does not always obey perfect reason? What if paradoxes are not just puzzles, but cracks in the structure of logic itself? In the end, the crocodile paradox does not offer a clear solution, because it is not meant to be solved. It is a mirror, reflecting the strange edges of reason where certainty dissolves. And in that moment, as the crocodile watches the parent struggle with an answer, it is no longer just a beast. It is a reminder that sometimes, no matter how carefully we think, some questions have no escape. The whole paradox. A whole is nothing. It is the absence of something, a gap in reality, a place where matter should be but isn't. And yet, despite being defined by emptiness, a whole undeniably exists. You can fall into one. You can dig one. You can even own one. But this raises a strange and unsettling question. How can nothing be something? This is the whole paradox, a philosophical puzzle that challenges our understanding of existence, absence, and the nature of reality itself. We talk about wholes as if they are real things. There is a hole in your sock, a hole in the ground, a black hole in space. But what exactly are we referring to? A sock is made of fabric. The ground is made of earth. Space is a vast field of matter and energy. But a hole? It is defined not by what is there but by what is missing. The paradox is deceptively simple. If a hole is nothing, then how can we describe its size, its shape, its depth? A hole in the wall can be measured, mapped, and even repaired. But what is actually being measured? The hole itself, or the material surrounding it? Suppose you fill a hole with dirt. The hole is gone, yet the dirt remains. Did the hole truly exist in the first place, or was it just an illusion created by the absence of material? This paradox has haunted philosophers and scientists alike. The ancient Greek philosopher Parmenides argued that non-existence cannot exist, meaning a whole, being defined by absence, should be impossible. Yet we see and interact with wholes constantly, meaning they must exist in some form. The problem deepens when we apply it to language. If wholes are real, then they should be objects we can count and manipulate. If they are not real, then why do we talk about them as if they are? Modern physics takes this paradox into stranger territory. Black holes, for instance, are among the most extreme objects in the universe, defined by their gravitational pull so intense that nothing, not even light, can escape. But if a black hole is merely an absence of matter, then why does it exert such a powerful force? How can nothing pull something? Even more disturbingly, black holes appear to store information, meaning that they are not just voids but structures with measurable properties. In this sense, a black hole is not merely an absence, it is an entity. Linguistics adds another layer to the paradox. If you remove all the cheese from a cheese sandwich, is it still a sandwich? If you remove all the water from a lake, is the hole left behind still a lake bed, or something else entirely? The way we use words shapes how we think about reality. But wholes resist definition. They are not objects, yet they have attributes. They are not matter, yet they change the world around them. Some have tried to resolve the paradox by claiming that wholes are not things but properties, the way wetness is a property of water. But this does not fully explain why we talk about wholes as if they exist independently. Others argue that wholes exist only as conceptual placeholders, labels we use to describe something missing. But if that is the case, then what happens when you fall into one? What happens when a hole is so large that it swallows stars? Ultimately, the whole paradox forces us to confront a deeper problem: can nothingness be real? If a whole is an absence, then does its presence contradict its own nature? The more we try to define it, the more it slips through our grasp, a void in logic itself. Perhaps in the end, wholes exist not in space, but in thought, gaps in understanding that, like the empty places they describe, can never truly be filled. The information paradox of black holes. At the edge of the universe, beyond the reach of light, lies one of the greatest paradoxes in modern physics, a contradiction so profound that it threatens to unravel our understanding of reality itself. It begins with a question that seems deceptively simple: what happens to information when it falls into a black hole? The answer should be straightforward, but it isn't. This is the information paradox of black holes, a clash between two of the most fundamental theories in physics, general relativity and quantum mechanics. On one side, Einstein's general relativity tells us that black holes are regions of space so dense that nothing, not even light, can escape. Once something crosses the event horizon, the point of no return, it is lost forever. On the other side, quantum mechanics tells us that information, the fundamental description of a system's state, can never be destroyed. But if information falls into a black hole and disappears, then something has gone terribly wrong. To understand why, imagine you throw a book into a fire. At first glance, the information in the book is gone, burned to ash. But at a microscopic level, the fundamental particles that made up the book still exist. In theory, if you had perfect knowledge of every interaction, you could reconstruct the book from the ashes. Information is never truly lost. It only changes form. But a black hole does not work like fire. When information crosses the event horizon, it is not merely scrambled, it seems to cease to exist. And here lies the paradox. If information can be destroyed in a black hole, then the entire foundation of quantum mechanics is broken. The laws governing the universe would need to be rewritten. For decades, physicists have struggled to resolve this contradiction. Some have argued that information is simply erased, but this would mean that black holes defy the fundamental principles of physics. Others have suggested that information is somehow preserved on the event horizon itself, encoded in an almost incomprehensible way. This idea led to the concept of the holographic principle, the idea that reality, at its deepest level, may function like a hologram, where three-dimensional information is somehow stored on a two-dimensional surface. But perhaps the strangest solution comes from Hawking radiation, first proposed by physicist Stephen Hawking. According to quantum mechanics, black holes are not entirely black. They slowly evaporate, emitting radiation over time. This process suggests that black holes do not last forever. Eventually, they shrink and vanish. But if a black hole evaporates, what happens to everything that fell inside? Does the information return, or does it disappear along with the black hole? Hawking initially believed that information was permanently lost, a conclusion so unsettling that it sparked one of the biggest debates in modern physics. Later theories proposed that information is somehow encoded in the Hawking radiation itself, leaking out in a form we do not yet understand. If true, this would mean that black holes do not erase information, but rather scramble and re-release it in an almost incomprehensible way, much like a burned book turning into smoke and heat, but still carrying traces of its original state. Yet the paradox remains unsolved. Some physicists believe that black holes might act as cosmic recycling bins, returning information in a form so transformed that it is effectively lost to us. Others suggest that information is never inside the black hole at all, but rather stored in the fabric of space-time itself. More radical ideas propose that black holes lead to parallel universes, with information escaping into dimensions we cannot perceive. The information paradox of black holes is not just a problem for physics, it is a problem for reality itself. If information can be destroyed, then the laws of nature are incomplete. If it is preserved, then black holes are not what they seem. Somewhere in the depths of the cosmos, an answer exists. But for now, black holes remain more than just cosmic voids. They are puzzles, swallowing not just matter and light, but the very fabric of our understanding. The self-reference paradox. There is a peculiar kind of statement that seems to fold in on itself, twisting logic into a contradiction that cannot be resolved. At first it appears harmless, just another sentence, just another idea. But as soon as you attempt to analyze it, it destabilizes reality itself. This is the self-reference paradox, the strange and unsettling result of logic turning back on itself. At its core, self-reference occurs when a statement, rule, or system refers to itself in a way that creates a logical contradiction. The most famous example is simple yet profoundly troubling. This statement is false. If the statement is true, then it must be false. But if it is false, then it must be true. The statement exists in a suspended state, forever trapped in an endless loop. It refuses to settle into either truth or falsehood, exposing a fundamental weakness in the way we define logic itself. But this paradox is not just a linguistic trick. It is a deeply unsettling flaw that extends far beyond words. It lurks at the very foundation of mathematics, philosophy, and even artificial intelligence. Consider Russell's paradox, which shattered the foundations of set theory in the early 20th century. Mathematician Bertrand Russell noticed a contradiction in how sets or collections of objects can define themselves. Imagine a set that contains all sets that do not contain themselves. Does this set contain itself? If it does, then by definition it should not. But if it does not, then it must contain itself. The entire system collapses into contradiction. In mathematics and logic, self-referential paradoxes threaten the very idea of consistency. This led to Gödel's incompleteness theorems, which proved that within any sufficiently complex system, there will always be true statements that cannot be proven. In other words, no system of logic can ever be complete. It will always contain gaps, unavoidable blind spots created by its own internal contradictions. The implications are staggering. If self-reference undermines the foundations of logic, what does that mean for our understanding of truth itself? Can we ever build a perfect system of knowledge if every attempt eventually collapses under its own weight? In the realm of artificial intelligence, the self-reference paradox is not just a theoretical concern, it is an existential problem. A machine programmed with strict logical rules can be trapped by self-referential loops. If an AI encounters a contradiction like obey this command where the command is ignore this command, it can be thrown into a computational deadlock, unable to proceed. Some theories even suggest that true artificial consciousness might be impossible without some form of paradox resolution, meaning that to truly think like a human, a machine must be able to handle illogical contradictions without breaking. And then there is the question of consciousness itself. What happens when the mind turns inward, trying to understand itself? Neuroscientists and philosophers have long debated whether self-awareness is inherently paradoxical. Can a mind ever fully understand itself, or does it become trapped in an infinite loop of self-reference, like a camera pointed at its own screen? Some have suggested that consciousness is nothing more than a recursive illusion, a process that continually references itself without ever arriving at an objective truth. The self-reference paradox is not just an abstract problem, it is woven into the very structure of existence. It appears in logic, mathematics, artificial intelligence, and even in the nature of human thought. It suggests that certain questions may never have answers, that some truths may always remain just out of reach. Perhaps the real paradox is this: if self-reference can destabilize reality, does that mean reality itself is built on something unstable? Or is it possible that paradoxes are not flaws in the system, but rather the only things keeping it together? Paradox of thrift. Most people grow up believing that saving money is a wise and responsible habit. Set aside part of your income, build a safety net, and ensure financial security for the future. On an individual level, this makes perfect sense. But what if saving, when practiced by an entire society, actually causes economic collapse instead of stability? This is the paradox of thrift, a counterintuitive phenomenon in economics that suggests what is beneficial for one person can be disastrous for everyone when applied on a large scale. At its core, the paradox reveals a strange contradiction. While saving money helps an individual accumulate wealth, widespread saving across a population can weaken the economy by reducing overall demand. It works like this. When people choose to save instead of spend, businesses sell fewer goods and services. As revenues drop, companies cut costs, often by laying off workers or reducing wages. Unemployment rises, people have even less money to spend, demand shrinks further, and the cycle continues. The very thing people fear, a worsening economy, ends up happening precisely because they acted cautiously to avoid it. To see this paradox in action, imagine a small town where most of the population works for a handful of businesses, perhaps a bakery, a clothing shop, and a furniture store. If the townspeople suddenly decide to save more money by cutting back on non-essential purchases, the bakery sells fewer pastries, the clothing shop sees fewer customers, and the furniture store has unsold inventory piling up. In response, business owners may lay off employees or reduce their wages to compensate for lost revenue, but those very employees are also the town's customers. The unemployed bakery worker now has even less money to buy clothes or furniture. The store owners in turn feel the downturn and cut back further. The cycle continues, and soon what started as a cautious effort to save money has triggered economic decline across the entire town. This problem doesn't just apply to small communities, it plays out on a national and global scale. During economic downturns, like the Great Depression of the 1930s or the 2008 financial crisis, people instinctively saved more and spent less. Businesses cut jobs, factories shut down, and the economy ground to a halt. Governments tried to intervene with stimulus measures, but the root of the crisis was a widespread collapse in consumer demand. The paradox was famously explored by the economist John Maynard Keynes, who argued that during recessions, increased saving is dangerous because it reduces the total spending needed to keep an economy moving. He proposed that governments should step in by increasing public spending to compensate for the drop in private spending. This is why, during economic crises, governments often introduce stimulus checks, tax cuts, or major public works projects to encourage people to spend rather than hoard their money. But this raises another uncomfortable question. If an economy depends on continuous spending to survive, does that mean saving is always a bad thing? Not quite. The paradox doesn't apply in times of economic stability when consumer demand is already high. In those cases, saving allows for investments that drive long-term growth, such as businesses expanding, banks lending, and individuals funding education or retirement. The issue arises only when saving becomes widespread during a downturn, creating a chain reaction of falling demand and rising unemployment. This paradox also challenges the idea of financial responsibility. If saving too much can hurt the economy, does that mean reckless spending is actually beneficial? In an extreme scenario, a society that embraces endless consumption could avoid recession, but at the cost of sustainability, debt would rise, resources would be exhausted, and economic bubbles would form, only to burst later. The paradox of thrift is not just about money, it's about the delicate balance between individual choices and collective consequences. The paradox reveals an unsettling truth about modern economies. Stability is built not on caution, but on the illusion of constant movement. When people stop spending, the entire system begins to unravel. It raises deeper questions about the nature of economic growth. If consumption is the engine that keeps everything running, is there ever a point where we can afford to stop? And if true financial security comes not from saving, but from spending, can an economy ever be truly sustainable? The Causal Horizon Paradox. There is a limit to what we can see, a boundary beyond which light has never reached us. This is the causal horizon, the edge of the observable universe. Beyond it there exist galaxies, stars, and entire cosmic structures that might as well be ghosts. We know they are there, but their light will never reach us. And if we can never interact with them, do they truly exist in any meaningful way? This is the Causal Horizon Paradox, a mind-bending problem that questions the very nature of reality and causality. If the universe is infinite, and if parts of it are permanently out of reach, then we are effectively trapped within a cosmic bubble, forever cut off from a vast majority of existence. And yet, physics tells us that the entire universe follows the same fundamental laws. But how can we claim to understand a reality that extends far beyond what is even theoretically observable? To grasp this paradox, we must first understand the speed of light as the ultimate cosmic speed limit. According to Einstein's relativity, nothing, not even information, can travel faster than light. This means that the farther an object is from us, the longer its light takes to reach us. But here's the problem. The universe itself is expanding, and not just expanding, accelerating. The further away a galaxy is, the faster it appears to be moving away from us. At a certain distance, space itself expands faster than the speed of light, meaning that any light emitted from those regions can never reach us. This defines our cosmic horizon, the boundary separating the part of the universe we can observe from the part that will forever remain unknown. But this raises disturbing implications. If two distant regions of the universe can never interact, then what determines the fundamental laws that govern both? Why should the laws of physics be uniform if the universe is permanently divided into isolated causal zones? If we can never verify what lies beyond, how can we ever claim to understand the totality of existence? And then there is the question of time itself. The causal horizon is not static. It changes over time. As the universe expands, more and more regions cross the threshold, drifting irreversibly beyond our ability to detect. Civilizations that might exist in those galaxies, if they ever did, will never be able to communicate with us. They might have seen our Milky Way long ago, but as time passes, our existence will fade from their view, as if we never existed at all. This paradox becomes even stranger when applied to the future. One day, even galaxies that are visible today will recede beyond the causal horizon. If the acceleration continues, the universe will eventually become a lonely void where every remaining observer is trapped within their own shrinking bubble of space. Over billions of years, entire cosmic structures will vanish, not because they cease to exist, but because they have become causally unreachable. The cosmos is not only expanding, it is erasing itself. But here's the real paradox. If we can never observe these regions, do they truly matter? Do they even exist in a way that is meaningful? This is not just a theoretical concern. It strikes at the core of physics itself. Our entire understanding of the universe is based on observable data. But if entire regions of reality are permanently hidden from us, does that mean our knowledge of the cosmos will always be incomplete? Some physicists argue that the causal horizon defines the limits of reality itself. Anything beyond it might as well not exist because it will never influence us. Others suggest that reality does not require observation, that the laws of physics must extend beyond our reach, even if we will never confirm it. But perhaps the most unsettling question is this: if the universe continues to expand, and if everything eventually slips beyond the causal horizon, then in the distant future will there come a time when nothing remains visible at all? A universe that once stretched endlessly in every direction could shrink, not physically, but in terms of perception, until all that remains is a tiny island of matter adrift in an eternal void. The Causal Horizon Paradox challenges everything we assume about space, time, and our place in the cosmos. It suggests that reality is not a single connected whole, but an ever-fragmenting collection of isolated regions, each one cut off from the rest as the universe races toward an unknowable fate. And if we are forever bound within a shrinking sliver of existence, then perhaps the greatest paradox of all is that the universe we think we understand may already be slipping beyond our reach. The Unexpected Exam Paradox. A teacher announces to their class, "Next week, there will be a surprise exam. You won't know which day it will happen until the moment it begins." The students, eager to outthink the situation, begin to analyze the claim. If the exam were to take place on Friday, the last possible day, they would know by Thursday night that it must happen the next morning, making it no longer a surprise. So Friday is impossible. Now, if Friday is ruled out, then Thursday must be the latest possible day. But on Wednesday night, realizing that the exam hasn't happened yet and that Friday is impossible, the students would conclude that the exam must take place on Thursday. Again, no surprise. Following this logic backward, they eliminate every possible day. If the test cannot be a surprise on Friday, it also cannot be a surprise on Thursday, or Wednesday, or Tuesday, or Monday. The paradox seems to leave only one logical conclusion: the exam cannot happen at all. Yet when the day arrives unexpectedly, the teacher hands out the exam. The students are caught completely off guard. The exam happens despite the seemingly perfect logic proving that it shouldn't be possible. This contradiction is the core of the Unexpected Exam Paradox, also known as the Surprise Examination Paradox, a problem that shatters our assumptions about logic, prediction, and knowledge. At its heart, the paradox plays with the idea of self-reference. The student's reasoning about the exam influences the very thing they are trying to predict. They assume that if they can logically determine when the exam will take place, then it cannot be a surprise. But this reasoning collapses on itself because the process of eliminating days only works if the exam doesn't happen before their deductions are complete. This paradox extends beyond a simple classroom thought experiment. It exposes a fundamental flaw in how we apply logic to uncertain situations. The students assume that their knowledge of the rules allows them to predict the future with certainty. But what if the act of thinking itself introduces an unavoidable blind spot? Consider this. The paradox suggests that logical reasoning may, in some cases, prevent us from accepting reality even when it is inevitable. The students' airtight logic prevents them from believing in the possibility of a surprise test at all, even though in the end their expectations are overturned in the most unexpected way. This principle is eerily similar to Gödel's incompleteness theorems, which reveal that even in the most rigorous logical systems, there will always be truths that cannot be proven within the system itself. Just as the student's logic seems flawless but ultimately fails, our own mathematical and philosophical structures might contain hidden contradictions, places where certainty crumbles into paradox. But the implications go even further. The unexpected exam paradox is not just about surprises. It reveals how prediction itself can be self-defeating. If we assume that the future is fully determined by logic, then we might overlook the very ways in which reality disrupts our expectations. The paradox raises an unsettling possibility. Perhaps there are limits to what can be known, not because of insufficient evidence, but because of the very nature of knowledge itself. Now consider this paradox applied to real life. Could a military strategist, a stock trader, or even a scientist fall into the same trap, believing they have ruled out all possibilities, only to be blindsided by the very event they dismissed? Could our ability to anticipate disaster or success be fundamentally constrained by the fact that our predictions influence the system we are trying to predict? This paradox forces us to question whether certainty is always possible. If logic itself can lead us into a blind alley, what does that say about our ability to predict anything with confidence? Perhaps some things remain unknowable, not because they are complex, but because knowledge itself cannot always be perfectly self-contained. The unexpected exam paradox is more than a riddle. It's a reminder that reality is not always bound by the limits of human reasoning. And perhaps, in the grander scheme of things, the biggest surprises are the ones we never saw coming. The Grelling-Nelson Paradox. Language is supposed to help us make sense of the world. It defines, categorizes, and structures reality, turning the chaos of existence into something we can describe and understand. But what if language itself is a trap? What if, buried within its rules, there exists a paradox so fundamental that it breaks the very logic it was meant to organize? This is the Grelling-Nelson Paradox, a problem that arises when words begin to turn against themselves. Imagine dividing all adjectives into two categories: autological words which describe themselves. For example, short is a short word. English is an English word, and polysyllabic has multiple syllables. Heterological words which do not describe themselves. For example, long is not a long word, French is not a French word, and monosyllabic has more than one syllable. So far, this seems straightforward, just a clever way to sort words. But then comes the question that dismantles everything. Is the word heterological itself heterological? If heterological is autological, it must describe itself. But that would mean it is heterological, a contradiction. If heterological is heterological, then it must not describe itself. But since being heterological means not describing itself, it must be autological, again, a contradiction. There is no escape. The moment you try to categorize the word, logic collapses. Language, the very system we rely on for clarity, turns into an impossible loop. The Grelling-Nelson Paradox is more than a linguistic oddity. It exposes a deep instability in the way we define things. Words are meant to act as containers of meaning, but what happens when a word tries to define itself? The paradox suggests that certain concepts simply cannot be classified in a consistent way, no matter how precise the rules seem to be. This paradox echoes a larger issue in logic and mathematics. Bertrand Russell's famous Russell's Paradox, which asks whether a set of all sets that do not contain themselves is part of itself, follows a similar structure. If such a set includes itself, it must exclude itself. If it excludes itself, it must include itself. The Grelling-Nelson Paradox applies this contradiction to language instead of mathematics, proving that even words, when examined closely, can create unsolvable dilemmas. But the implications go even further. If some words defy classification, what does that say about language as a whole? Could it mean that certain truths about the world are inherently beyond definition? Is it possible that some ideas exist outside the limits of human thought simply because our language fails to capture them? Philosophers and logicians have debated whether paradoxes like this reveal fundamental flaws in human reasoning or whether they are simply a byproduct of the way we construct systems of classification. Some have attempted to resolve the Grelling-Nelson Paradox by arguing that certain words should not be considered legitimate adjectives in the first place, sidestepping the problem rather than solving it. But even this approach feels unsatisfying, as it suggests that contradictions in logic must simply be ignored rather than understood. In a way, this paradox mirrors the problems of self-awareness and self-reference. Just as language struggles when a word tries to describe itself, do we struggle when we try to understand our own existence? When we ask, "What am I?" or "What is consciousness?" are we running into the same kind of paradox, where the act of defining something alters the thing being defined? The Grelling-Nelson Paradox serves as a reminder that some questions might never have a satisfying answer, not because we lack intelligence, but because language itself might be a flawed tool for understanding reality. And if that's the case, then perhaps the greatest paradox of all is this: can we ever truly know what we cannot express? The Quine Paradox. There's a certain kind of riddle that feels like a trap the moment you step into it, a sentence that coils in on itself like a snake eating its own tail. You think you've understood it, but the more you turn it over in your mind, the stranger it becomes. The Quine Paradox is one of these linguistic black holes, a paradox that challenges the very idea of self-reference and definition. It's a sentence that refuses to be pinned down, a statement that simply by existing questions the meaning of existence itself. At first glance, it seems innocent enough. The Quine Paradox, named after the philosopher and logician Willard Van Orman Quine, is built around a sentence that defines itself in a way that breaks language. Imagine a sentence that reads, "is false" when preceded by its own quotation. That's it. That's the statement. But now, let's take it seriously. What happens when you try to complete it? If you were to quote the sentence and place it in front of itself, you'd get something like, "This sentence is false" when preceded by its own quotation. Now, take a step back and try to analyze it. If this statement is true, then it must be false, because that's what it literally says. But if it's false, that means it must be true. It's a perfect loop. A sentence that seems to say something, yet refuses to resolve into anything meaningful. This is where the Quine Paradox separates itself from other self-referential paradoxes, like the classic Liar Paradox, where someone says, "I am lying." The Liar Paradox creates an infinite loop between truth and falsehood, but the Quine Paradox is different. It's not just about contradiction, it's about the breakdown of definition itself. The moment you try to define the sentence, it slips out of your grasp, like trying to hold water in your hands. To make things even stranger, this paradox isn't just an abstract curiosity. It has profound implications for logic, philosophy, and even computer science. At its core, the Quine Paradox demonstrates how language can be structured in ways that defy conventional meaning. Sentences are supposed to communicate something, to point to a truth or a falsehood, but this one refuses to do either. It builds its meaning out of its own existence, making it both the subject and the object of its own definition. In logic and mathematics, this type of paradox becomes even more unsettling. In formal systems, paradoxes like this suggest that self-reference can create statements that cannot be evaluated as true or false. This is a serious problem because much of logic depends on being able to classify statements cleanly. If you introduce a statement that cannot be resolved, you create a kind of logical black hole, something that defies categorization and breaks the rules. You might wonder, does this matter outside of abstract philosophy? Actually, yes. In computer science, self-referential statements like the Quine Paradox are directly related to issues of recursion and self-replicating programs. In fact, a quine in programming is a piece of code that, when run, outputs its own source code. This is a practical application of the same strange logic, information that defines itself without external input. But maybe the most fascinating thing about the Quine paradox is how it makes us question our own thinking. We rely on language to make sense of reality. We assume that words and sentences exist to communicate meaning. But what if a sentence simply exists to describe itself? What if meaning is something that collapses the moment we try to grasp it? It's unsettling to think about. A sentence that doesn't tell us anything except that it exists. A statement that refuses to be defined because its definition is its own structure. And yet here we are trying to define it anyway. So the next time you hear something that feels like it means something profound, ask yourself, does it truly have meaning, or is it just a linguistic trick, looping forever in its own reflection? Maybe the Quine paradox isn't just a problem in language, but a mirror showing us the limits of our own understanding. The St. Petersburg Paradox. Imagine a game so simple that anyone can play it, yet so paradoxical that it threatens to break our understanding of value, probability, and rational decision-making. A game where the possible winnings stretch into infinity, but the price to play seems impossibly small. A game that on paper should make you bet everything you own, yet in reality, most people wouldn't even risk a few dollars. This is the St. Petersburg Paradox, a thought experiment that exposes the fragile relationship between mathematical expectation and human intuition. It begins with a coin toss. You pay a fixed fee to enter, say, $10. A fair coin is flipped. If it lands on heads, the game ends and you win $2. But if it lands on tails, the coin is flipped again. If heads appears on the second toss, you win $4. If tails appears again, the game continues, with the potential payout doubling each time. $8, $16, $32, $64, stretching toward infinity. At first glance, the expected value of this game, what a rational person should be willing to pay, seems limitless. The reasoning is straightforward. There's a 50% chance of winning $2, a 25% chance of winning $4, a 12.5% chance of winning $8, an even smaller chance of winning $16, then $32, then $64, and so on. Mathematically, when you sum all these possibilities, the expected payout diverges to infinity. In other words, if people were purely rational and followed probability theory alone, they should be willing to pay any amount to play this game. $100,000? $1 million? Everything they own? The expected value suggests it would be worth it. But here's the paradox. Almost no one would actually do this. In reality, most people wouldn't even pay $20 for a chance to play, let alone bet their life savings. So where does the contradiction lie? If the math suggests one thing, but human behavior suggests another, what does that say about our understanding of value and rationality? The St. Petersburg Paradox was first proposed in 1713 by the Swiss mathematician Daniel Bernoulli, who saw in it a fundamental flaw in how traditional probability theory calculates worth. Bernoulli suggested that the problem wasn't in the numbers, but in how people perceive those numbers. His answer was diminishing marginal utility, the idea that as wealth increases, each additional dollar becomes less valuable to us. For example, if a billionaire wins $1,000, it barely changes their life. But if a struggling worker wins $1,000, it might mean rent, groceries, or medical bills paid. Because of this, people don't value money linearly. The difference between $2 and $4 feels much more significant than the difference between $1 million and $2 million. This insight led to the development of expected utility theory, which suggests that instead of maximizing raw probability, people maximize their perceived benefits. But even this does not fully solve the paradox. Because the St. Petersburg game is structured with potentially infinite rewards, no matter how much you adjust for diminishing returns, the expected value still trends toward infinity. Even modern decision theory struggles to explain why rational people refuse to pay large amounts to play. So what does this tell us? Some argue that the paradox reveals a fundamental flaw in probability theory itself, that real-world decisions cannot be based on mathematical expectation alone. Others see it as proof that humans are simply not wired to think rationally when it comes to probability and risk. And then there's the deeper philosophical question: if we can't trust mathematical expectation to guide our choices, what should we rely on instead? The St. Petersburg Paradox may seem like just a strange betting game, but its implications stretch far beyond gambling. It highlights the disconnect between logic and intuition, between theory and reality. And perhaps, most disturbingly, it suggests that the numbers we use to model the world, even in the most objective mathematical sense, may not be as reliable as we think. The Barber Paradox. Language is meant to bring clarity, to describe the world in ways that make sense. But sometimes, words turn against themselves, creating contradictions that shouldn't exist. A sentence can follow all the rules of logic, yet lead to an impossible conclusion. The Barber Paradox is one of these traps, a paradox that emerges not from numbers, time loops, or quantum mechanics, but from the very structure of language itself. It starts with a simple definition: the smallest number not definable in fewer than 12 words. At first, this seems reasonable. Some numbers, like 1 or 7, can be described with a single word. Others, like 100 or 1000, take 2. But eventually, as numbers grow larger and more complex, it should take more than 12 words to define some of them. There must be a point where a number cannot be fully described without exceeding the limit of 12 words. But here's the problem: we just defined it. The smallest number not definable in fewer than 12 words is itself a description under 12 words long. That means this number is simultaneously undefinable within 12 words and defined within 12 words, a contradiction that should not be possible. The moment we try to precisely capture this boundary, language collapses on itself, leaving us with a paradox. The Barber Paradox was first proposed by the mathematician Gottlob Frege, but it was later given its name by Bertrand Russell, after a librarian named G. Barry who noted the linguistic problem. Russell, who was already wrestling with logical paradoxes in mathematics, saw something deeper in it, a fundamental flaw in how we use words to describe complex concepts. This paradox reveals something unsettling about human language. We assume that words have precise meanings, that definitions set clear boundaries between what something is and what it is not. But the Barber Paradox exposes a hidden flaw. Sometimes our definitions create feedback loops that collapse the meaning entirely. The phrase "not definable in fewer than 12 words" ceases to be meaningful the moment we successfully define something using it. It gets even stranger when you extend the logic further. If we can construct a paradox just by manipulating definitions, how many of our everyday statements contain hidden contradictions? How many of the concepts we use to navigate the world, numbers, identity, even knowledge itself, are built on linguistic shortcuts that might break under scrutiny? Some have argued that the Barber Paradox is not a true paradox at all, but merely an illusion created by vague language. Maybe the problem isn't in the definition itself, but in how we treat self-referential statements as if they can be precise. Others believe it points to something much deeper, a limit to logic itself, where no system of reasoning, no matter how carefully constructed, can avoid contradictions entirely. Either way, the Barber Paradox stands as a warning. It reminds us that language is not perfect, that even the most careful definitions can lead us into impossible loops. It challenges us to question the words we rely on, because sometimes the very act of defining something is what makes it undefinable. The Friendship Paradox. We tend to think of our social lives as balanced. Some people have large circles of friends, others prefer solitude, but on average, we assume most people's social experiences are fairly typical. Yet there is a mathematical truth lurking beneath the surface, one that distorts our perception of how connected we really are. It's called the Friendship Paradox, and once you see it, you can't unsee it. It begins with a deceptively simple observation. Your friends, on average, have more friends than you do. This sounds wrong. After all, friendship is reciprocal. If you're friends with someone, they're your friend too. Shouldn't friendships distribute evenly across a network? And yet, if you were to go through your list of friends and check how many connections each of them has, you'd likely find that most of them are more socially connected than you. How is this possible? The paradox arises from the structure of social networks. Highly connected individuals, those with many friends, are more likely to be in your circle than people with few connections. A person with a vast network of friends is simply more visible in social spaces. If someone has 500 friends, they appear in far more people's social circles than a person with only 5 friends. This means that, statistically, most people's social experience is shaped by the presence of those who are more connected than they are. Think about a crowded party. The host, who likely has a large social network, is seen by nearly everyone in attendance. But the quiet guest standing in the corner, who knows only a handful of people, might go unnoticed. Social visibility is unevenly distributed, and this distortion makes it seem like everyone around you is more socially active than you are. The implications go beyond just friendship. This paradox affects every kind of network, from professional connections to online influence. On social media, for example, people tend to follow celebrities, influencers, and content creators with large audiences. This skews perception. Even if the average user has only a few followers, they mostly see people who have thousands or even millions. The result? It feels like everyone is more popular than you, even when that's not statistically true. This effect has consequences beyond social comparison. In epidemiology, for example, diseases spread faster through well-connected individuals. If an illness enters a community, it's more likely to be transmitted through highly connected individuals, making it seem like everyone around you is infected before you even catch it. In economics, wealth often follows a similar pattern. The people you interact with may seem wealthier than you, not because most people are rich, but because wealthier individuals have broader social and professional circles, making them more visible in the system. It even plays into politics and cultural influence. If ideas spread through well-connected individuals, it might feel like everyone believes something simply because the most vocal or influential people are repeating it. This is why trends, political opinions, and cultural movements can seem far more dominant than they actually are, not because they're truly widespread, but because they're concentrated in the most visible parts of the network. The friendship paradox forces us to question how we see our own social world. It reminds us that our perspective is not neutral, that the people we surround ourselves with are not necessarily representative of the larger population. When you feel like you aren't as connected, as popular, or as socially active as those around you, it might not be because you are lacking. It might just be a mathematical illusion. The Preface Paradox. An author stands before an eager crowd at a book signing, smiling as they hold up their latest work, a carefully researched, painstakingly edited book filled with facts, arguments, and conclusions. Every claim has been double-checked, every assertion supported with evidence. And yet, in the book's preface, the author humbly admits, "Despite my best efforts, there are almost certainly some mistakes in this book." This single sentence is the key to a paradox, one that seems trivial at first, but reveals a fundamental contradiction in human reasoning. The paradox begins with a simple observation. If the author truly believes every individual statement in the book, then they must believe the book is entirely correct. Yet, if they also believe that mistakes are inevitable, then they must believe that at least some of the statements in the book are false. How can both beliefs coexist? The contradiction lies at the heart of the Preface Paradox, a challenge to our understanding of rational belief and knowledge itself. To break it down, consider what it means to believe something. Rational thinkers strive to hold only justified, well-supported beliefs. If the author has done their due diligence, they should believe every claim they have written. After all, to include a statement they don't believe would be dishonest. And yet, past experience has shown that even the most rigorous works contain errors. No book is perfect, no argument airtight. The author's general knowledge tells them that human error is unavoidable. The paradox emerges because these two beliefs, believing every statement in the book while also believing some must be wrong, are logically incompatible. At first glance, the solution seems obvious. Perhaps the author doesn't actually believe every single statement, but instead merely accepts them with high confidence. But this only shifts the problem rather than solving it. If rationality demands that we proportion belief to evidence, then we should never be completely certain about anything. However, we often act as if we are stating facts, making claims, and constructing arguments with the full conviction that they are correct. The paradox highlights the strange tension between intellectual humility and epistemic commitment. One proposed resolution comes from distinguishing between local and global reasoning. The author believes each individual statement based on specific evidence, but their belief in potential errors is not about any single statement, it is about the book as a whole. It's a meta-belief based on the general understanding that humans make mistakes. In this way, the contradiction dissolves. Each individual belief is rational on its own, but the larger recognition of fallibility operates on a different level. Yet, this explanation doesn't sit well with everyone. It raises a deeper question. If we always admit that some of our beliefs must be wrong, then how can we ever be justified in claiming certainty about anything? If even the most careful logical thinkers accept the possibility of error, then is all human knowledge fundamentally uncertain? The Preface Paradox serves as a reminder that rational belief is not as simple as it seems. We must navigate the fine line between intellectual confidence and humility, certainty and skepticism. And so, as the author signs another book and hands it to a reader, they may wonder, is there a mistake on this very page? The Raven Paradox. A scientist stands in a field staring at a single black raven perched on a fence post. He nods and scribbles something in his notebook. This moment, seemingly ordinary, is actually a glimpse into one of the strangest paradoxes in logic and the philosophy of science, the Raven Paradox. At first, the idea seems simple. All ravens are black. That's a reasonable statement, based on observation. But how do we actually confirm that it's true? The answer, according to logic, is through inductive reasoning, by seeing more and more black ravens. Each black raven we encounter strengthens our belief that the statement is correct. This is where things take a turn. The philosopher Carl Gustav Hempel in the 1940s pointed out something unsettling about how logical confirmation works. It starts with a basic rule in logic. If a statement is true, then anything that contradicts it must be false. For example, if the rule all ravens are black is true, then its opposite must also be true. Everything that is not black is not a raven. That seems harmless at first, but here's where the paradox kicks in. If a green apple is not black, and it is also not a raven, then according to logic, the apple actually confirms our statement about ravens. Yes, you heard that right. By looking at a green apple, you are supposedly confirming that all ravens are black. This means that every time you see a red chair, a blue book, or a yellow sunflower, you are, strangely enough, gathering evidence that all ravens must be black. This sounds absurd. After all, a green apple has nothing to do with ravens. And yet, according to the laws of formal logic, it contributes just as much confirmation to the hypothesis as actually spotting another black raven. The problem isn't the logic itself, it's the unsettling conclusion it leads us to. If this were true, then a scientist trying to prove that all ravens are black wouldn't even need to look at ravens at all. He could just spend his time collecting data on every non-black thing in the universe and claim that, indirectly, he was proving the color of ravens. It's a paradox because it follows the rules of reasoning perfectly, yet it defies common sense. This issue highlights a deeper problem in how we define confirmation and evidence. In science, we usually trust observations that are directly relevant to what we're testing. If you want to prove that all swans are white, you look at swans, not bricks or pine cones. But the Raven Paradox forces us to ask what actually counts as evidence. Should logic always take precedence over intuition, or does our natural sense of relevance matter? Many philosophers have tried to resolve this paradox. Some argue that in theory, the green apple really does count as evidence, but just very weak evidence compared to actually seeing a black raven. Others say the paradox is a flaw in our assumptions about confirmation itself, suggesting that real-world science doesn't follow such rigid logical rules. Either way, the raven paradox remains a haunting puzzle in the philosophy of science. It reminds us that even the simplest statements, like all ravens are black, can spiral into unsettling contradictions when examined closely. And so, as the scientist in the field watches the black raven take flight, he wonders, what is truth if even a green apple can confirm it? The elevator paradox. You step into a building, press the elevator button, and wait. It arrives, the doors slide open, and strangely enough, it's already occupied. It feels like this happens almost every time. The elevator always seems to be coming from above, rarely from below. You might not think twice about it, but this everyday experience hides a subtle yet fascinating paradox. First proposed by physicist George Gamow, the elevator paradox plays with our expectations about randomness and probability. If an elevator moves freely between floors, stopping as needed, then you might expect to catch it coming from below just as often as from above. But that's not what actually happens. The key to the paradox lies in how elevators behave in busy buildings. Imagine a skyscraper with dozens of floors. More people tend to gather on the lower levels, lobbies, office spaces, food courts, where foot traffic is highest. This means that the majority of elevator trips start from the lower floors going up. As a result, elevators spend more time traveling upward from lower floors than downward from higher floors. But here's where it gets counterintuitive. If elevators spend more time higher up because they are frequently called from below, then when you press the button, the elevator is more likely to be coming down rather than up. This gives the illusion that you always find yourself stepping into a downward-moving elevator, even though logically it seems like it should be a 50-50 split. A similar effect happens in random sampling. Imagine you're standing at a bus stop, and buses are supposed to arrive every 10 minutes. In reality, delays cause gaps, so when a bus does arrive, it's more likely that you've been waiting during one of the longer gaps rather than one of the shorter ones. The same applies to elevators. The more time an elevator spends on upper floors, the more likely you are to encounter it coming down. The elevator paradox is a reminder that perception doesn't always match probability. What feels like an annoying quirk of modern life is actually a hidden rule of statistical physics in action. So the next time you step into an elevator that seems to have come from above yet again, remember it's not just bad luck, it's math. After 3 hours of unraveling the strangest, most mind-bending paradoxes, one thing is clear: reality is far stranger than it seems. These puzzles don't just challenge logic, they force us to rethink everything we assume about time, truth, free will, and even existence itself. But the real question is, which paradox left you questioning reality the most? Let me know in the comments. And if you enjoyed this deep dive into the impossible, consider subscribing for more. There's always another paradox waiting to be explored.